Welcome, everybody. We'll just wait another minute for people to accrete and then we'll get started. Okay, so I see the numbers are still climbing, but I think we'll get started here in the interest of time. Try to keep things on schedule for people popping in and out. And so on behalf of the Gemini staff, welcome to day 3 of the 2021 Virtual Gemini Observatory Science Meeting. And so my name is Janice Lee, and I began serving as Gemini's chief scientist back in March of this year. And as mentioned yesterday and the day before, all the talk sessions every day begin with this round of announcements. It's to help to get people oriented, to help our registered attendees get the most out of the Whova app, the platform that we're using for this meeting, and out of the way we've scheduled the program and the content. So we're at the halfway point. On the first 2 days, we really set the stage. We had a state of the observatory talk from Director Lotz. We had overviews of our current, future, and future instrumentation suite. We had an overview of the diversity of proposal modes available at Gemini Observatory to support your research. And then we talked about brown dwarf and exoplanet science and instrumentation, including IGRINS 2, Maroon X, GPI 2. And then we started yesterday with a session on galaxy evolution in AGN. And of course, we've had a good deal of social interaction on the Whova platform. And not only do we have a chat group on pet photos, but now we have a chat group on plant photos as well. And so you can see Steph's guava tree here next to Inger's goat now. This is a nice feature of the Whova platform. If you go to the community tab, you're able to set up your own chat groups. So have a look. Today, on day 3, we'll wrap up our extragalactic science with an invited talk on AGN. And then we'll begin a deeper dive into the future of the Gemini instrumentation suite in AO with dedicated talks on the upcoming instruments. At the end of the day, we'll cap it off with a planning workshop for targets of opportunity. And then tomorrow, our final day, we'll complete our TDA. We'll go into a session on TDA science and Gemini planning for next generation time domain astronomy. At the end of the meeting, we'll have a talk from Director Pat McCarthy on the future of Gemini within the context of NOIRLab. And we'll have a panel discussion. And this is just an announcement that after the panel discussion on the future of Gemini concludes, we'll be having a conference photo. So if you wish to participate, stick around until then, and we'll have folks unmute their video and take a few screenshots, and we'll have a photo of this virtual conference. Proceeding with the reminders for those of you who have joined us for the past couple days, you know this well now. For those of you who are just joining us now, each day we have chat sessions with speakers before and after the talk sessions begin. To sign up to reserve a slot, or if you just want to drop in and say hello, if you want to drop in to ask a question, follow up on something you heard in the talk, You go to the Whova agenda and there's a Google Doc link there with all of the links to the chat rooms as well as the schedule. So please have a look and take advantage of that. And finally, a reminder of how we are conducting Q&A during the workshop. If you go to the Zoom application, the platform, for each session, there is a dedicated Q&A tab. Type your questions there as you have them throughout the talk, and our moderator, our chair, will go ahead and review them and ask them at the end of the talk during the 5-minute Q&A session. The contents, the questions, as well as the discussion will be persistent throughout the meeting, as well as over at least the next month. So if you wish to follow up on discussions, those pages are available to you. If you have any problems at all during the meeting, you can pop into the Ask Organizers Anything section on the Whova Community tab. Or if you're having trouble with the Whova platform, feel free to email the LOC at gemini21vsm@noirlab.edu. So with that, I will take a look for questions on the Whova app before I introduce today's chair. Any questions? Okay, great. So to introduce today's chair, we have with us Henry Rowe, who is the Gemini Deputy Director. He's currently based on Gemini South. His research interests are atmospheres and surface in the outer solar system. And he's well known for studies of the atmosphere of Titan, for example. And he's also interested in binary Kuiper belt object dynamics. So Henry, are you there? Ready to take it away?
Yes, thank you, Janice. And thank you everyone else behind the scenes here who's making this conference run so smoothly these last few days. We really appreciate it. So, well, good morning to some, good afternoon, good evening. And I think we even have a few people where it might be good middle of the night to you. Thank you for joining us from all over the world. We're excited to have you here today. Janice gave you, I think, all of the reminders that I have here in front of me regarding how we're going to do questions and answers in Whova, so I won't belabor those. Just remind the speakers that we'll have the 2-minute warning stars. They'll start appearing on the slide until you acknowledge. And everybody else, please come enter your questions into Whova so we can have some interesting discussions after each talk. And with those details out of the way, onward. Our first speaker today is Rogemar Riffel of the Universidade Federal de Santa Maria in Brazil. And he'll be discussing AGN and feedback in the wrap up of that session. So Rogemar, if you're ready, you're sharing your screen and please take it away. And Rogemar, if you haven't, you might leave your video on for you too, if that's possible. Is he unmuted?
Yeah,
I'm sorry,
yeah.
I'm not hearing anything.
Can you hear
Okay.
now?
Yes, I hear you and see you, and I see your slides now. Perfect.
Okay.
Thank you.
Well, I thank the organizers for the opportunity to share our recent results based on Gemini observations of nearby active galaxies. And the outline of this talk will be a short introduction. Then I will show some results on electron temperature distributions in 3 nearby luminous safer galaxies. I will present some results on ionized outflows from GMOS IFU observations of 30 local AGN. And finally, I will show some results based on NIFS observations of the molecular and ionized gas in the central region of nearby AGN and list my conclusions. So we know that the bulk of star formation and galaxy formation occurred in the first 3 giga years of the universe. And we know that supermassive black holes from the observations, for examples of high redshift quasars, that supermassive black holes evolve together with their host galaxies from the black hole mass and central bulge mass correlation. And from simulations, we know that supermassive black hole form in the densest regions of the galaxies in their centers. Can you?
Rojima, hold on one second. I think we might be having a technical issue with your slides advancing. We are still seeing your title slide. I apologize. There, now we're on slide number 4.
Yeah, you're just not showing, you're just showing the actual screen. I think you need to start the presentation.
No, I just started the presentation. Can you see my full screen?
No, we're seeing the window with, we saw it for a second.
Yeah, maybe I'm sharing the wrong window. Just a minute. Maybe this one. Can you see full screen right now?
No, we're still just seeing the, looking like you're editing your slides instead of the actual presentation.
And now?
No, I don't know if you want, see, we saw it for just a second. You did something and then we saw it it flashed up for just a second.
Yeah, I'm going to share screen. Then maybe I have to, just a moment. No.
Maybe share a whole display instead of just an app.
No.
No, same thing. All right, so I don't know if you want to just for time or whatever, just advance that mini window. Oh, there we go. There we go.
Yeah.
That's it. You got
Okay.
it. You're good.
So one of the main main goals of the extragalactic astronomy is to identify processes that transform galaxies from star forming to quiescent. And a way to quench star formation is by AGN feedback. And here I will focus mainly on AGN winds, which can be effective in suppressing star formation in some cases. AGN outflows are multiple phase phenomenon, and especially the most massive and molecular phase can produce shocks and affect the star formation in the host galaxies. However, the multi-phase nature of AGN outflows is still not well understood, and questions like that, what are the geometries and the kinetic powers are still open. AGN winds and shocks are hardly observed and hardly spatially resolved by observations of distant galaxies, but we can resolve AGN winds in nearby galaxies where supermassive black holes are accreting at lower rates. And an ideal tool to map AGN winds is by using integral field spectroscopy. And here we use optical and near-infrared integral field spectroscopy of the inner kiloparsec of nearby galaxies to map AGN winds. Most of the results, all of the results I will show here are published by the AGNIFS team in collaboration with several people here listed. All of them are listed here. And I will start by showing some results on the electron temperature distributions in the inner kiloparsec of 3 luminous safer galaxies. The motivation behind these 2 papers published this year is that shocks from AGN outflows may affect the ionization structure and the electron distribution. especially in regions where the AGN ionizing photons are shielded by nuclear obscuration. However, there are no spatially resolved maps of the electron temperature in the narrow-line region of AGN, and we used high signal-to-noise ratio Gemini IFU observations to map the electron temperature in 3 luminous ciphers. These 3 galaxies are Mcconaughey 79, Mcconaughey 348, and Mcconaughey 607. They were selected from a previous work by Freitas et al. Just because they present the O3 for 363 emission line and its flux distribution is spatially resolved by Gemini's observations in each of these 3 galaxies. And so that we can use this line together with the strong 015007 emission line to measure the electron temperature. And here I show the maps for the 3 galaxies for Mcconaughey 79, Mcconaughey 348, Mcconaughey 607. In each panel, the black line shows the AGN ionization axis, obtained from the O3 flux distribution. And we observe that the highest temperature values are observed mainly away from the AGN ionization axis, outside AGN ionization cone, at least for Mcconaughey 79 and Mcconaughey 348. We also see a trend of higher values away from the AGN ionization axis, while for Mcconaughey 607, the temperatures are smaller and consistent with photoionization models' predictions of AGN. In order to investigate the origin of these high temperature regions, we looked at the gas kinematics using the W80 parameter of the O3 5007 emission line. This parameter is just the width of the line that contains 80% of its total flux. And we see that the highest velocities here, the highest W80 values, are observed co-spatial with the highest temperatures. And when we plot W80 against the electron temperature, we see that there is a trend of increasing W80 with increasing electron temperature, providing kinematic signature that shocks are producing the high temperature values we observe. In addition, the O1 over H alpha line ratio correlates with the electron temperature. And we know that this line ratio is a shock tracer, so this provides additional support that shocks play an important role in the observed temperature distribution ionization, this structure, at least in Mcconaughey 79 and Mcconaughey 348. So just summarizing these 2 papers, we use Gemini IFU to observe the central kiloparsec of 3 nearby galaxies. We use the O3 flux distribution to define the AGN ionization axis, and we found that the highest temperature, electron temperature values are outside the AGN ionization cone, and we attribute this to shock emission gas. A possible physical scenario for that is that these shocks are produced by AGN winds, which have a wider opening angle than the AGN ionization cone. Here, the blue arrows are showing the AGN, represent the AGN winds, while the green lines show the AGN ionization cone. So that inside the AGN ionization cone, photoionization dominates the production of the line emission, while outside the AGN ionization cone, we are able to detect shock emission gas. Moving the second part of my talk, we used GMOS to observe 30 local AGN hosts. 13 of them were observed in the single slit mode, which provides both the blue part of the spectrum, including the blue emission lines and the red emission lines, and 17 objects were observed with the true slit mode, where only the red part of the spectrum is available, but the field of view is twice than the one for the single slit mode. For each galaxy in this paper led by Dutra et al., we present emission line flux distributions, velocity maps, centroid velocity map for each galaxy, and W80 maps for O3 and N2 emission lines for each galaxy, as well as line ratio maps and electron density maps measured from the sulfur 2 emission lines. We define regions, spaxels, where outflows are observed as those with W80 larger than 600 kilometers per second, and have H-alpha equivalent weight larger than 6 angstroms. And when we compare the electron density distributions of the outflowing gas in orange here with the gas in the disk, we see that the electron density of the outflows are higher than the density of the gas in the disk. We compute the mass outflow rates by computing the masses using the H-alpha luminosity. We assume that the velocity of the outflow is W80 over 2, and the radius of the outflow is the distance of the maximum distance from the nucleus where a spaxel with outflows is detected. And here we plot the outflow rate against the AGN luminosity. We plot our results here together with some results from the literature. And we see that our sample populates the low luminosity end of this relation. And we see that the scatter in the lower luminosity is higher than for the higher luminosity AGN. Moving on to the near infrared. In the near infrared, we can use the hydrogen recombination lines, Paschen beta in bracket gamma, as well as iron 2 emission lines to map the ionized gas kinematics. And we can use the molecular hydrogen lines in the K-band to trace the hot molecular gas. In a first study in the near infrared, we present J and K-band NIFS data of 6 safer galaxies. For each galaxy, we present the emission line flux distributions, and we construct the emission line ratio, near infrared emission line ratio diagnostic diagram, iron 2 over Paschen beta against A2 over bracket gamma. Here, red points are typical AGN values, while green points are higher than typical values observed in AGN. We see that the typical AGN values are observed mainly closer to the nucleus, while outside the nucleus we detect higher line ratios for both iron 2 over Paschen beta and A2 over bracket gamma. In order to investigate what's the origin of these high line ratios, we define a function, an emission line ratio function, which is just a function of these 2 line ratios here, and plot it against the W80 for the iron 2 emission line. And we see that there is a trend of increasing of this function with the increasing of the W80, indicating that the high line ratio, the green spaxels here, are the emission of these spaxels that is produced by shocks. This green region corresponds to about 29% of all spaxels in these 6 galaxies, while for the red spaxels, we see high velocities, which are consistent with outflows, but emission lines are produced likely by the AGN radiation field. In a second work in the near infrared, we present K-band data of 36 AGN, which are all the AGN with NIFS data available from the Swift BET catalog at redshift smaller than 0.1. 18 objects are type 1 and 18 are type 2. And they have very similar flux luminosities and redshifts. For each galaxy, we present flux maps and H2 over bracket gamma line ratio, and we construct an excitation map with the smallest line ratios consistent with star formation and the highest one by shocks. I will skip this one as well, this one. In the second work, we are looking at the gas kinematics in the same sample by presenting W80 maps, centroid velocity, and peak velocity. We define a kinematically disturbed region, likely due to outflows, just based on the values of W80 for the H2 over 330 kilometers per second, for bracket gamma over 400 kilometers per second, which are represented here by the red regions. We compute the mass outflow rates for the ionized gas and for the molecular gas. And for each galaxy here, there are 3 distinct symbols, which are just different assumptions to calculate the mass outflow rates. We detect outflows in 27 objects in ionized gas and 20 objects in molecular gas. We also were able to construct radial profiles of the mass outflow rate here for the ionized gas. And we see that the peak of the outflow is the average value is 230 parsecs from the nucleus. And we compute also the kinetic powers of the outflows. Usually the outflows are not powerful enough to quench star formation. They are lower than 0.5% predicted by theoretical studies. And again, the scatter of the relation is higher here in the low luminosity end than the higher luminosity end. And here are my conclusions. We detect that shocks are important, play an important role in the electron temperature distribution. They are more important in regions away from the AGN ionization axis. We detect ionized outflows in 80% of the studied galaxies, with outflow rates from 10 to the -4 to about 100 solar mass per year. Hot molecular outflows are seen in 55% of the galaxies, and these outflows are not powerful enough to suppress star formation in the host galaxy and may just redistribute the gas within the galaxy. Thank you.
Thanks, Rojamar. Let's see. I don't see any questions in the chat, so let me ask a question of what, of the capabilities we have coming at Gemini in the future. What are you most looking forward to for this work? What would be most helpful to your future ambitions here?
Well, that's an interesting question, and I haven't thought about it. We still have some galaxies to be observed to complete our sample with NIFs. And likely we will not be able to conclude it before NIFs leave the telescope. And likely we will use the Junior's IFU to complete our sample, but I don't know, we will need likely IFU data. So in the near future, we will still be using GMOS.
And I see one question in the chat here that I'll ask you, and if you can give a brief answer. Do you have GMOS and NIFS data from the same galaxies? If yes, does the iron 2 bracket gamma shock indicator follow the TE distribution?
Yes, we have NIFS data for some of these galaxies. And yes, we see that the iron Paschen beta line ratio is higher in the same region where we see the high electron temperature, for example, for Mcconaughey 79.
Great. Thank you again, Rojamar. Excellent talk. I appreciate it. Next up, we have Alan Mcconaughey of NRC Hertzberg to tell us about the next new instrument at Gemini, GHOST, which we look forward to getting assembled, installed, and commissioned on Gemini South as soon as the current pandemic conditions allow. So Alan, I see you're sharing your slides. If you would turn on your video and unmute yourself, please go ahead. Thank you. Oh wait, now we're back to a preview of your slides rather than the display mode.
Yes, I had to switch my mute off. Can you hear me all?
Yes, I can hear you and I see your title slide now. Perfect.
Fantastic.
Thank you.
Thanks very much. So we very much hope that this will be one of the next go-to workhorse instruments for the Gemini observatories. We are all very proud of it, the group who have worked on this now for several years, many of whom are in the audience today, I see. GHOST, the Gemini High Resolution Optical Spectrograph, is a next generation fiber-fed high-res optical spectrograph for Gemini. It's a collaboration between the Gemini observatories, of course, teams in Australia, particularly at AAO and the ANU, and here also in Victoria at NRC, the Hertzberg Research Centre. Now, Michael Ireland is the project scientist for this. I'm also on the science team and sort of the project scientist for the spectrograph part of the spectrograph. The Australians, in particular AAO, have been working on the fiber feed and the CAS unit. The software is done by ANU, and the instruments spectrograph system is done here in Victoria. Now, you're all aware of the sort of science that can be done, and indeed GHOST has grown out of a long-term need in the Gemini community for this capability. There were white papers submitted quite some time ago now, which sort of stimulated all of the requirements for it. But I think this also highlights really the challenge that the instrument team have taken on, and I think really done very well with, which is we are a latecomer to a well-developed field. There are lots of high-resolution spectrographs on 8-meter class telescopes. Keck High-Res, ESO had some great spectrographs, Magellan, Mike, and many others. And so therefore, given that, we don't just want to be another one out of a collection. We want to be the best. We want to be the go-to high-resolution spectrograph for the entirety of the astronomical community, all of the Gemini partnership, and frankly, we hope everybody wants to collaborate with the Gemini partnership in order to be able to use this instrument. And so in terms of what the requirements have translated to, in terms of what you're going to get at the telescope, this is a high-resolution spectrograph where the entirety of the optical wavelength from slightly blueward of 360 nanometers out to beyond 1 micron is available in a single shot. There's no need for multiple setups. It's not a narrow wavelength range. You get the entirety of the optical spectrum at once. Indeed, at low resolution, or we'll call it standard resolution, because that's R55,000, you can do it with 2 objects simultaneously and about a 7 arc-minute field of regard. You can also go to even higher resolution, close to R of 90,000, and observe a single target at that resolution, again across the entirety of the optical wavelength range in one shot. This is a highly stable instrument. I'll go into some details about how we make sure that it's going to be very easily calibratable over both short and long-term timescales. And while we haven't explicitly designed this to, enable the measurement of precision radio velocities, and by that I mean meters per second, a HARP-style spectrograph, we do believe that over the years we will be able to get pushed down towards those sorts of numbers. And this is going to be, I think, a really fascinating and really interesting science-enabling capability for the observatories. As you'll see at the end as well, this has all been done with the thought that we are going to be observing lots of very faint targets. So we have very high throughput and a very good observing efficiency. You're not going to be wasting lots of time acquiring a target and things like this. We can make all these claims because while we are late to the field, we've also therefore been able to benefit from increases in technology that have happened over the past decade, indeed which have happened during the design and fabrication of GHOST. So for example, the 6x6K detectors, which allow us to get the entirety of the spectrum on just a blue and a red detector. The fact that we can actually do that is because we can now have these large format, high quantum efficiency coatings, which were not available a decade ago. This couldn't be done. UV enhanced silver coatings, the sort of throughput, the losses on each reflection now are very, very small. And again, we have a lot of very good blue efficiency for Gemini, even within various reflections, and even though the UV is so hard to do well. As you'll see, our enclosure and the entire setup of this instrument is highly stable, temperature stable as well as vibrationally stable. And due to some really great innovations in the optical design led by John Pasder and colleagues here in Victoria, we've got some really nice features that really increase the image quality. For example, the field curvature of the cross disperser is essentially non-existent. This means you have fantastic image quality. Again, I'll show you what that means in practice. The cross dispersers that we're using are fantastic. They were, I suppose, perhaps one of the last that Kaiser Optics has produced. As for those of you who know about the Spectrograph world, Kaiser Optics has decided to not do astronomical BPH gratings anymore, which is a massive loss to astronomy. But we have some fantastic gratings that they've helped develop for us. The camera designs are very nice. One of the things for those of you who are used to looking at shell spectra, you will notice a very nice feature in the spectra that I show you towards the end of this talk, which basically just makes the data format much easier, hopefully makes the data reduction much more intuitive and practical as well. And the optical mechanics is likewise very nice. The concept is this: it's a fiber-fed instrument. So you have the cast unit, where you have the IFUs. These go down approximately, I think it's about 30-meter fiber cable down to the QD room, where the NOIRLab, sorry, where we have the whole bench spectrograph system. At the telescope, we have two IFUs. The first IFU is the two black hexagons that you see, as well as the smaller one. And then at the bottom, you have a second IFU. You'll notice there's a bunch of different fiber configurations there. So what you have here is you have two standard resolution IFUs, both about sort of 1 arcsecond, just under 1 arcsecond projected onto the sky, as well as some sky fibers. These can be positioned to target two different objects. Or you can do that mode, or you can use the other mode, which is the high resolution IFU bundle with, on the other set of IFUs, you have the high resolution sky fibers that go with it. Now, what happens is that these miniature IFUs, the slit is reformatted through the fibers to produce two different slits. And so on the left, you see the slits corresponding to the standard resolution mode. On the right, you see the slits corresponding to the high resolution mode, where you see in the standard resolution mode, you have the two black object fibers, and in between them, you have some sky fibers. And for the high resolution mode, you have the high resolution object fibers, you have some sky fibers, and you also have a simultaneous calibration fiber where you can send down a thorium argon lamp as well in order to sort of really do some very nice wavelength calibrations. The actual spectrograph that this gets fed to, we describe as a box in an isothermal box. So this was the CAD rendering of it in the NOIRLab in Gemini, and inside the ghost enclosure is another enclosure surrounding the bench. That outer enclosure is fantastically temperature stable. It uses these very nice NTC thermistors in such a way that the heat is evenly distributed around the entirety of that outer box. That inner box itself, that bench is vibrationally isolated, is incredibly stable. What this means, and in fact, this is what it looks like assembled in Victoria. What this actually means is as the ambient temperature outside, and this was outside in Victoria, where the temperature is not the most stable, you'll see, despite those large variations, the actual variation spread by multiple temperature sensors distributed throughout that box, there is no variation. It's incredibly stable down to the levels of almost millikelvins. It's really a very, very nice system. The optical design, again, there's been some really nice improvements in the design here that we are the first, I think, to actually implement, in particular the white people relay design, with the result that 80% of the energy actually gets concentrated in a single pixel. So a single pixel is about 15 by 15 microns, and we're able to put sort of 80% of the energy that goes down the fiber into one of those pixels. It's really quite remarkable. And again, all of these are very high efficiency optics. Again, I'll show you what this looks like in practice. This is the design, but of course, reality is what matters. The optical mechanical design, again, is a very stable, vibrationally isolated system. And again, you can see it actually as it was constructed in Victoria. Detectors, for those of you who are used to looking at detector QE curves, you'll notice that for both the blue and the red CCD there, these are incredibly high efficiency. So the actual delivered efficiency is the yellow dots. And you can see you're above 90% wavelength efficiency, everywhere except the extreme red and the extreme blue. This is really nice detectors. You can in fact see I'm sure he's smiling under that mask, the face of Greg Burley, who was really one of our go-to detector peoples. And this was before masks were the thing to wear. But this was when we were putting things together. And again, it's just some really, really nice components that we're able to use here. And the first slide used a very, very high quality piece of paper in the lab back in 2019. We had this assembled. And there's John Pazda, who has been sort of one of the lead engineers and the lead optical designer for all of this. I believe he's on the call today as well, showing the first spectrum that we got through GHOST. We fully assembled everything in the lab at Victoria, and we were able to do a lot of tests in the lab. So all of these are real data. This is the blue and the red CCD images of what happens when you put a mercury lamp down GHOST. And so this allows you to see the spectral format, where because of the limited number of mercury lines, we were also able to sort of see exactly what wavelengths we get. The free spectral range is indicated by the diamonds on the left and right of each shell. You will notice the different orders. There's a lot of overlap. So for the blues go from 63 up to 96. And the red goes from 35 up to 65. So again, there's 3 orders of overlap there as well. We can also confirm that we have spectral coverage from 359 nanometers out to just slightly beyond 1 micron. Again, very broad wavelength coverage. So I mean, there's a tremendous amount of data here anytime you get a GHOST spectrum. Trying to advance my slide, and it's not. So just 1 second. One moment, and my computer has frozen. I'm not sure why. There we go. The delivered image quality is fantastic. What we did here was we used a tiny fiber, a 10 micron fiber. Recall that the pixels of GHOST are 15 microns. That means essentially all of the light should be concentrated in a single pixel if we've done things correct. And when we zoom in and then put things on a logarithmic or square root scaling here, you'll notice that, yeah, actually more or less all of the light is concentrated in just a single pixel. And so this is, again, remarkably nice image quality. And it really will mean that we can get this very, very nice data format, very, very efficient spectrograph. Such that, in fact, when you actually look at a full slit, this is the red detector where we've zoomed in on some slits here. You can actually see that, recall that this single slit is in fact multiple fibers, and you can actually see the individual fibers that make up the slit in each of these. But further, those of you who are used to looking at shell spectra, you'll be aware that the shell orders are slightly curved, and as they're curved, the slit ordinarily tilts and changes its tilt as you move across the detector, as you move across each order. That's not the case here. John was able to come up with some incredibly clever techniques which completely cancel out. So the curvature is introduced, the tilting of the slit is introduced at various points in the design. And he's actually done it such that they all sort of cancel each other out, such that the slit basically stays aligned with the CCD columns from left through to right. Again, making the data format just that bit easier to understand and to interact with from the sort of science use perspective. Ironically, GHOST has no ghosts. We did our best to burn a hole in the detectors by putting a very, very bright lamp down the fibers. And this is what you get, some really nice illuminated slits, but you'll notice there's almost no ghosts. And in fact, the only ghost that a few of you might see down at the very bottom of the red is in fact outside of the wavelength range that we were supposed to design for anyway. So who cares? bottom line of this is, again, this will help us push down to those very faint limits, push down to those really faint signatures. And so this is going to be a very nice thing indeed. Empirical measurement of the spectral resolution means that we're getting to a resolution of about 55,000, and we're critically sampled everywhere in the standard resolution mode, similarly in the high resolution mode. And just, I see Henry's reappeared there. So just very briefly, this is the signal noise of the observation of a star, about the 10th magnitude star, but it just shows the relative throughput of Grace's, high-res, UVES. What we were designing for, the requirement was the solid line, the solid red line. What we were designing for was the red dash line. In the end, what we've actually measured, and again, this is through empirical measurements in Victoria, is the gray line in this plot. The gray line is the actual throughput. This is involved with combined with the Gemini telescopes. So you will see we are significantly better throughput than high-res, UVES, Grace's as well. Grace's is great in the red, but Ghost is great everywhere. So this is going to be really, I think, very nice. We shipped it in February 2020. It was making its way down the coast of the Americas. Everything was great. Then there was a global pandemic, which was not actually on our risk register. We will put our hands up to that. So most of the major components are currently sitting at Gemini. We still have the very precious optical components here ready to ship by air just as soon as we are able to figure out how to travel down there. We can't wait to do it. I think everybody's very keen to get this on the telescope. We think it's a fantastic instrument. We have some fantastic a science program as well. One of the things that the science team is able to do a science program where all of the data is going to be available to the entire community, because essentially troubleshooting the entire system, because obviously there's going to be a few hiccups as we put something on the telescope. So we have a science program which we hope to run over the first several semesters of GHOST, where we want to be looking at very faint stars in the galaxies surrounding the Milky Way. Stellar chemistry will be a key part of GHOST. Also, Michael Ireland will start investigating this instrument for actual planetary observations. It should be fantastic. Please, any questions you have for me now, I'm happy to answer them. I will also be doing one of these chat sessions later on, so please feel free to join me then. Thank you.
Thank you, Alan. That was excellent. And yes, it's somewhat scarring seeing those containers again. I'm glad we at least have the instrument on the summit now safely, and we look forward to getting it on the telescope. Let's see. We do have a few questions here. What is that just went past me? What is the setup time for each object and sky configuration?
Very short. I can't recall, but it's measured in a few minutes. I don't recall the exact number, perhaps one of the others online will, but no, it's very short. And I should also note as well, a lot of that setup time, a lot of it's usually spent acquiring objects as well. And the IFU has already been commissioned, actually. It was able to be commissioned independently of the bench spectrograph. So we already know that which can be one of the biggest time sinks for observations, we already know that works very well as well. So it should be very efficient.
Excellent. Let's see, another one is the data reduction pipeline ready?
The data reduction pipeline works perfectly with our simulated data, which is to say, of course, there's going to be some iterations on it. This is work with the ANU and Michael Ireland in particular. I hope you lead that. That's going to be one of the major things that both the science team, the commissioning team at the telescope, and also the Gemini Observatory will be working on during and immediately after the commissioning. So we think we have a good pipeline, but again, integrating it once we actually get confronted with real data, because even when we make our data imperfect, we make it imperfect in perfect ways, right? So that's just reality. So we have every reason to believe that we should have a good version of the pipeline very soon after we start getting the first data from GHOST, and that will of course be part, I believe, of the whole Dragons environment. And in fact, I'm sure we'll be learning about that very, very shortly.
Great, thank you, Alan. Given the time, we need to move on. There are a couple more questions in the chat that perhaps you could try to answer offline after the session, and people can continue to ask questions in that chat after the session.
Great.
So thank you again, Alan. Next up, we have Massimo Roberto of Space Telescope Science Institute to tell us about the future instrument Scorpio, which is currently under construction and will be brought to Gemini South. Roberto, if you are able to share your screen and unmute and bring your video on. I see your video is online now, and we'll just wait for your screen to be shared, and then you can begin, please. Perfect. I see your first slide, so please continue. Thank you.
But you're still muted.
Okay. Can you hear me?
Yes, that's perfect. Thank you.
Okay, thank you. Sorry for messing up. So I'm going to give you an overview of Scorpio, the capabilities of the instrument and the status report of where we are right now. So Scorpio is an acronym, is a nice acronym for spectrograph and camera for observing rapid phenomena in the infrared and in the optical. And this already summarize what is the main goal scientifically, which is the follow-up of transients. This is the instrument, the facility instrument that has been conceived, requested to perform follow-up of LSST and in general time variable phenomena, follow-up and monitoring as well, so pretty long-term type of work, but it's also a powerful workhorse for the observatory, as you will see, a very efficient instrument. I'm trying here with the first slide to put the list of the main players. Probably it's not exactly complete. There is people that goes in and out, of course, in a long-term program. But it's distributed across the United States, Europe, and Chile largely, with a nice integration between us and the Gemini team. The next slide, this one, summarizes some basic science goal. Of course, you can imagine how wide and how much will explode this field in the next decade once LSST comes up to speed. We are sitting next door on the same mountain, so this is the ideal place to capture immediately, minutes after, the most interesting objects that may be detected, together with, again, general science. What are the capabilities of Scorpio? Scorpio is a broadband, multiband imager and spectrograph. Scorpio has, the actual Scorpio, the animal, has 8 legs, and we also have 8 channels. The 8 channels in imaging are reproduced basically in the most exact way, the standard astronomical bandpass, the LSST and the Roman bandpasses, GRIZ, the visible, and the standard Y, J, H, and K short band in the infrared. The field of view in imaging is 3 by 3 arc minutes, and I don't know, for someone like me, it's sort of the field of view of Hubble images. So it's not very wide field, but it's good. It's pretty good. Seeing limited, of course, and the pixel scale is 0.18, which is sort of ideal. 0.80 by 3 by 3, which means 180, means a field of view of 1000 by 1000 pixels in all 8 channels, both the infrared and the visible. In spectroscopy, the 8 channel convert to a very long slit of 3 arc minutes length, and all put together, once you attach all the spectra, you have a 24,000 pixel long slit spectroscopy of the sources that you have targeted. This typical resolution is around 4,000 with the default slit, which is about half an arc second, 0.54, which is sampled with 3 pixels. What are the main capabilities? The main capability is the rapidity of reconfiguration between imaging and spectroscopy. You can really, in a couple of minutes, move from one to the other. You have a very rapid target acquisition, and this has been pushed to the limit, adding rather recently in the project a slit viewing camera that very efficiently allows you to see where is your target on nearby targets and offset on your object. And then we have a sort of a new and a little bit crazy shutterless mode for ultra high speed imaging. We can do movies at crazy speed, of course, a narrower field, but we can do 50 milliseconds long-term exposures, or even burst mode, where you get for a fraction of a second images at 3 millisecond exposure. Something, must be very bright your target, but is a capability that we have implemented for the visible channel in particular. The instrument looked like this. Is a big piece of metal. It's 2 meters long, about 2 tons, almost flirting with the limit of mass and the center of mass that we have at the telescope, but is within the envelope, and is built as a dual instrument. Basically, it's shown here. If you zoom in, you see that there is a top bench, which is the infrared system, and the bottom one, which is a clone, like a specular image, which has the infrared, the visible channel. So Y, J, H, K are on the top. The light goes in the viewer first, and then is reflected down and walks to the optical channel through a series of beam splitters. We will see. This is a sketch again of the top and bottom reverted channels. The design is pretty similar, and is basically, the idea is a cascade of dichroic or beam splitters, both in the visible and in the infrared. Once you have 3 beam splitters, you create your 4 channels, actually your 8 channels. The first one splits the visible from the infrared, and then you cascade in the other 4 and 4. This is basically how it works. The light comes in from the left. This is the infrared channel, and goes through a set of mirrors and beam splitters to be spread wavelength by wavelength. The shortest wavelengths are always those that are reflected. The long wavelengths pass by, and in this way you trim your light and you populate your 4 arrays in the infrared. The same is basically happens in the visible. This is the bottom part. So the light goes from this hole here, which is a second exit window from the top viewer. And so going through this hole, enters in the lower level, and then walks on the optical bench parallel to the infrared on the top. And again, you can see the same type of structure. Beam splitters, mirrors, beam splitter, mirrors, and you get the 8 channels at the same time. This is the basic idea. The band passes, again, we tried, there is imaging and spectroscopy. Let me tell you about the imaging. The imaging here at the bottom, through a close matching of the beam splitters and the filter that are added to optimally select the bandpass. The bandpasses really reproduce the standard GRIZ bandpasses that have been adopted on LSST with the highest precision we could attain. And then the Y, J, H, and K are the standard one for the infrared wavelengths with the standard gaps in the OH absorption bands between J and H and K, and Y and J also. For spectroscopy, what we have done instead, since there is no real bandpass to respect, we try to have the maximum coverage in spectroscopy, and therefore, when we go in spectroscopic mode, we remove the filters and we put gratings, VPH gratings, that give us full coverage without gaps in the visible up to the J band, basically. And then we have, again, we cover the same bandpasses. But even in K-band, we move a little bit farther. The background here raises a little bit. This is not an infrared viewer, an infrared instrument with a cold pupil, a cold pre-optics, let's say. But you go up to 23, 2 micron and 35, basically, which is pretty red for a visible instrument. The observing mode, the detectors. As you can imagine, there is now we have 8 systems that we have to feed with light. The detectors are rather large, I would say. For the CCD, we use the 4K by 4K E2V systems, and for the infrared channel, we use the Y2RG with the standard cutoff at 2.7 micron. And here is in this cartoon, they are sketched, and you will see that in the imaging mode, we only illuminate a very small part of the central area, the 1000 by 1000 pixels. And this is the 3 by 3 Archimedes field. So there is a lot of state of the detector that is not used. Let me tell you that the black areas on the CCDs here are areas that are just never illuminated because the CCDs are masked with metal at the surface. This is because their structure is uses the frame transfer capability for the rapid acquisition mode. So we only illuminate with the green area. We could illuminate with the green area, but there is a field stop on the telescope focal plane just at the beginning of the instrument that really limits the 3 by 3 blue areas here. This is the field of view in imaging. When we go in spectroscopy, instead, we put the long slit in the middle, and then we use the entire horizontal 4000 pixel and 2000 pixels in the visible and in the infrared respectively. And in this way, we get our full coverage at the resolving power 4000 about in the channels. Then there is this one, which is the third one, is the high-speed imaging. We can put on the focal plane a smaller mask, which is only 18 arcsecond wide. This means that we can take an exposure and move the charges immediately out of the exposed region in the dark. We can do another exposure and move again. So we use the detector as a storage area as we integrate snapshots. And as long as you are slow enough that you can transfer the data out, you can continuously take very short exposures of this area. And this is about a 50 milliseconds continuum movie mode, high speed mode. However, if you want to go even faster, you can go faster and you can just store the charge on the detector. At some point you feel you don't have enough pixels to store what we have done, but you can do burst mode, and that can be as fast as 3-4 milliseconds per exposure. So there is here a new regime. There is actually a couple of instruments that try to reach these limits, and we have now this capability expanded over the full U to K bandpass, basically. So it's something new for very rapid phenomena, transients, bright as well, but it's something that you may want to explore. And this goes exactly in the direction of time variable events. Now, let's see if I can go farther here. Okay, so a key element here is the focal plane mechanism, the first mask that we put immediately after the viewer window, which has, of course, a number of gadgets on top to select a long slit, field, to this horizontal mask to do the fast readout. An important part, and this was the late addition I was mentioning, is the slit viewing camera. We have the possibility of giving you 7 masks with different slit sides, 2, 3, 4 pixel wide, 6, etc. And what we have is next to the mask, there is a little reflected aluminum coated surface that reflects the off beam. So you can immediately see what you have around your slit, which means you point your telescope, your target hopefully is within this field of view because the telescope points well enough. And then you can, with a little move, offset the target into the slit and be immediately measuring without having to take images and data acquisition. The slit viewing camera gives you acquisition together with monitoring, of course, of the good tracking, etc. We can read these detectors in several ways, of course. If you want to go very fast, you can trigger the detector at 1 megahertz per pixel. So it's really a very low duty cycle to read each pixel. The read noise in this case becomes higher, is 8 electrons instead of 4. But basically, you can see here that we have conventional standard imaging. The 1K by 1K image can be read in about 5 seconds with exquisite readout noise. This is the standard way of observing with CCDs. And in spectroscopy, you get slower, you have more pixels, but you have, again, excellent. 4 is sort of an upper limit, I believe. We will be closer to 3. But when you go fast, then you can go at 1 megahertz per pixel. You pay something in readout noise, but your readout time really drops. And then depending on how you read, if you use the mask, if you store the charge on pixel or you take it away, there is here a number of combinations. I have no time to go into the details, but you can really implement very fast readout times. And even in spectroscopy, you can benefit. Again, you need very bright sources, but imagine, I don't know, a solar system body that is rotating, you may want to try that. For the infrared, similarly, we have different ways to read. The single sample, as you may know, is sort of noisy because there is the reset, the KTC noise. So people normally does the double correlated sampling, which is something of the order of 15 electrons noise. But you can do the either forward or up the ramp sampling. Up the ramp sampling is our nominal way of reading, and we can then push the readout noise with multiple samples down to a few electrons, CCD-like, and have extremely good defense against saturation, against cosmic rays, etc., etc. So this is the standard way to operate. Now, you can imagine that when you observe in the UV, that you may want to have very long exposure in the blue, there is no moon, and you push 45 minutes. And at the same time, you have the infrared, where every 30 seconds you need to read and maybe dither a little bit, the sky is changing. You need to do some magic with the operation mode. And this is where you need to compromise as well, because depending on where your prime science is, you may push in one direction or in the other. But in general, you can imagine that long exposures with the CCDs will correspond to shorter exposures with the infrared detectors, and they must be just generally synchronized, so they all end at the same time when you decide to dither your telescope or to offset your source within the slit. This is a rather complex system that we are implementing, and in this way, from this point of view, the collaboration with the Gemini staff, crafting the best possible concept document of how we will operate. This is a critical part, and we are still defining the last details. But we have a pretty good idea of how these things is going to work, and how we can see. And of course, the electronics is built in such a way that we can synchronize and implement all these different observing modes. I want to tell you something about where we are right now. We have completed the design done. We are past critical design review, and we have been in the last couple of years into the manufacturing and sub-assembly, basically getting the pieces from the company, or cutting the pieces, putting together the elements of the system. We are almost done with this. And I will show you now a set of eye candies, basically, to demonstrate that we have hardware, almost all of it, in-house. And the next step will be the system-level integration of this such a complex system. Will be started in US. Everything will be shipped to Spain, where there is the main contractor for the optics. And then we'll come back once everything is assembled for the final integration and the performance, environmental test, flipping the instrument back and forth, see, flexures, etc. That part will come back to the US, and then we plan to ship to Gemini in February 2024. If we are late, I admit, because of COVID, mostly because of COVID. There have been delays from the manufacturing places, the company providing these systems. They had issues entering in their place, and sometimes even the company builds a lens, needs to have the coating or the blanks. There are cascades effects that have delayed us, like everybody else. Unfortunately, we were in this manufacturing phase in the last 2 years, but we use this time also to refine our concept of operation, software, etc. We didn't waste any time, honestly.
Massimo, if you could wrap up in just the next minute or so, we are nearing the time.
I am done because I'm basically done. I just want to scroll here through this picture to show you that the system that we have elements. This is basically for me and for you. There is no more PowerPoint. These are the optical cameras from Officina Stellare in Italy. They have, the infrared cameras. This is how we did the infrared testing of these systems. These are the visible part from France. Here we have 4 lenses pending, and they will also integrate the systems in the next couple of months. This is one of those that have delayed a little bit. other optical elements, the VPH grating, the grease, the filters, everything is coming together. And here is just a collection of the various, these are the beam splitters. You can imagine how many parts we have to put together, the relative mounts. And then the big pieces around the cryostat, the anti-vibration mount for the cold head. We have two cooling head to keep everything at 100 Kelvin, if you are curious. The camera heads for the CCDs. The CCDs are locally cooled down, not within the viewer, but there are like 4 little viewers. And these are the thermal links that have been appearing. And then the big titanium pieces. There is a mix of titanium, magnesium to keep it light. This is titanium. These are the brackets that keep the instrument in place. And this is the viewer that is coming up nicely and being built. Yeah. This is a big piece of stuff. And anti-vibration mounts. My conclusion, Scorpio is at the end of the manufacturing. We are going to integrate the system in the next couple of months. We had issues with COVID, but we managed to do nice work through that. I will underline the collaboration between us and the Gemini staff. This is a complex instrument. It's critical to get together and plan everything with the most experienced people, with this Gemini Observatory about operations. And the date is in 2.5 years from now will be shipped at the telescope. 1 year to integrate in Spain, 1 year to finalize everything, and then we ship. February 2024 is the time at the moment where is when we plan to ship everything.
Thank you, Massimo. Yeah, thank you. I'm sorry, we're a minute or so over. There is at least one question in the Whova chat, if you would be willing to, after the session, go in there and answer that and any other questions that people have. Thank you. It's fabulous to see the hardware coming together in spite of the challenges we've all faced in the last 1.5 years or so. Next up, we have Kathleen Labrie from Gemini, who will tell us about the Dragon's data reduction software project status and direction for the future. If you are, Massimo, could you stop sharing so that Kathleen can share, please?
Absolutely.
Thank you so much. And Kathleen, yes, I see your video and I see you're unmuted. So please, once you're able to share, go ahead. Thank you.
I'm on it. Go. Has it start? I don't see.
I see your screen, but not your.
Okay. Normally there's the green square. You can see my slides now.
I do see your slide now. Yes, perfect.
Excellent.
Thank you. Please proceed. Thank you.
Okay, so here to talk about dragons. I want to start with just a quick status, just to remind people that we're currently in a hybrid mode. We have dragons publicly released for all imaging data, all the facility instruments that we currently have. And if you have spectroscopy data, for the time being, you still have to use the Gemini RF package. But that is going to change. And currently, we are working on GMOS long slit support. It's split in two big projects. First, the quick look version, and then the science quality version. The quick look version, it's fully implemented and testing is underway. I was doing that this week, the last 2 weeks, and this week between the sessions. So it is proceeding well. And as I said, this is what's coming up. It's going to be released in the next couple months, I would say. It says December to February. I certainly hope I can at least release dragons sooner than that. It's for quick look. That means it's not science quality. We haven't vetted the science quality yet. That's actually coming up as part of another project. But what this new dragons will offer, well, the quick look, but it fits in an observatory project to do time domain astronomy. So internally, at least, it will come with two new tools. One to automatically create some calibrations, process calibration that we can use to reduce at night imaging data and also GMOS long slit spectroscopy data. At first, this is really just for target of opportunity data. I'm not saying that we won't expand it in the future, but initially, as we get our feet wet in that domain, we're going to concentrate on the TOs. This tool called FIRE, the Fast Initial Reduction Engine, will be run at night. So when a TO comes in, the data is observed, it will trigger FIRE. FIRE will, as soon as the sequence is done, it will start reducing, and within minutes, it will upload the extracted spectra to, for example, to the archive for the TOPI to go and retrieve. Again, this is not science quality, but in the context of TO, where as you take the data, you want to know, well, is this really a cool target that I really want more data on? Do I have enough data on this one? Is it really the redshift 1 million that I'm expecting, or is it just a redshift 0.3 that I don't care about? So this is the aim of this reduction, this quick look reduction, to try to guide the TO decisions. So this is coming up real soon. Also, what we're working on, and I estimate it's about 90% of the code is implemented, so it's very, very far along. It's the science quality. So obviously it builds on all the quick look tools that we have, but it has additional correction, like we're going to do the cosmic ray rejection, the slit function correction, and also one big item for the science quality version of the GMOS long slit support is the interactive tools. And I have screenshots at the end of the presentation of the tools that we've created. So currently we have 6 for one for flat normalization, the sky subtraction, wavelength calibration, extraction, and of aperture and the trace, then the sensitivity function. Note that all this actually runs non-interactively, but for science quality, often you really need, depending on your program, the condition of the sky, sometimes you really need to go and tweak to really optimize your reduction. So that's why the interactive tools are part of the science quality package of this support. And you were very close to actually start the science verification, and it will take some time. Personally, my worst case scenario is we release something, you publish a great paper, and then you have to retract it because we screw up. So I really want to make sure that once we release, we would ourselves use it for our own science. So currently the schedule is about a year from now that it would be publicly available. Next in line is going to be the near infrared long slit. So you see the progression. We're really building the mode, the support on top of the previous tools. And in the case of the near infrared long slit, well, a lot of the GMOS long slit code will be reusable. So unlike the Gemini RF, where there's a lot of code duplication, with Dragons, we really try to build on top of what we already have. So it means a bit of an investment at the beginning to write the tools that can be reused. But as we build this foundation, all the new development will come faster. So on top, for the near infrared, the 2 big items that we expect will be the sky subtraction, because it's done differently in the near infrared compared to the optical, and of course the telluric correction. We hope to be able to launch this in early next year, January. We just need, for the people who currently are working on the GMOS long slit for science quality, to finish the work they have to do there in order to move to the next project, which is the near infrared long slit. So yeah, it's gonna come for about a year after the GMOS long slit with the science. And here I see for the near infrared, it's science quality. It will also come with a quick look version. And really looking far ahead, our optimal goal is to actually remove our dependency on RF. Because as I have another slide about compatibility with various operating systems, we really need to remove this dependency. So when it comes to supporting the other instruments that we have, the near infrared IFU will be next. It's an image slicer. So that will cover NIFs, G-NIRS, and part of the motivation to bring this one up is the GearMOS project, which is also an image slicer. So if we can have some of the core generic tools in time for when GearMOS start their data reduction software, then it will be a very nice synergy between what we need to do and what they have to do. Following that is going to be the MOS for F2 GMOS, and GMOS IFU will probably be the last mode that we will address. As mentioned before, the GHOST pipeline is already written for Dragons. Scorpio, we're working closely. It's going to be written from that for Dragons. Some code is already in place. So this is progressing well. And I do mention the visitor instruments. We have some visitor instruments who want to start using Dragons. I've started working with the MaroonX people. There's some discussion with regarding Halopeke and Zorro. So basically, Dragon's infrastructure is quite flexible to a variety of instruments. Regarding the operating system, just a note to remind people what our current status is. When it comes to Dragons, Linux, we're not aware of any issues. Mac Intel, the Intel chip, we're not aware of any issues. The Mac M1, we haven't really formally tested it. Part of the issue here is we need all the dependencies that we're using must also work on M1. And until recently, I think there was some issues there. I saw a post about 2 weeks ago that somebody successfully installing a bunch of astronomy software on the Mac M1. So I'll have to have a look at that, and we need to test it. When it comes to Gemini IRAF, then it becomes a bit more complicated. Fortunately, Linux, still no issues. Mac Intel, if you run a somewhat ancient OS, so 10.13 and before, it will run natively. But starting with 10.14 and up to now, you must use a virtual machine that James Turner put together. So if you go to our website, it's going to lead you to a page that tells you how to download it, how to set it up. So you really need to use that VM. And it's because Mac removed their 32-bit libraries. For the Mac M1, it is a mess. So we've done some work trying to get the VM to work, but it is very, very messy. So stay tuned. We cannot make any promises whether we will succeed or not, but there's some fairly complicated issues here. And just honestly, I say come to my Dragons workshop tomorrow, and you'll have a little demo of how it runs. But if you're brand new to Dragons, just to give you an idea what the typical workflow is you download your data from the archive, you create your list, and we have tools to really speed things up. If you've reduced data with the Gemini IRAF, you might have used gem list, and you have to know which image number to put into, and then it will create a list for you. Well, none of that with Dragons. We make sure that it's a lot easier. Then you configure a calibration database that will allow automatic association of the process calibration. And then you just go, and what I have on the right is an example of the actual commands that you would have to put in to go from raw data, including calibration, all the way to science. That's all you would really have to type. And we also have an API if you want to code all this. And here's an example just to show you. I said that the code was basically all done, all implemented. So that's a GMOS long sit quick look, run completely hands off. Start with your raw data, and that's the 2D stack. It will stack in spatial and wavelength, size subtraction and extract. If you have more than one source, it will detect the sources and extract them all. And just for the details, standard bias correction, flat correction, QE, mosaic, distortion correction. The wavelength calibration is automatic, and it's very robust. Sky subtraction, the registration, as I said, spatial and in wavelength, the stacking, automatic extraction, spectrophotometry calibration is also automatic. So, and all this is done with, in this case, just 2 sampling, one for the mosaic and one at the very end when you align things in stack. And this is what our new interactive tools will look like. So you see it's a much more modern look. It's web-based. For those who are technically interested, we're using bokeh. So underneath is JavaScript with what we code in Python. That's how they look. And with that, just self-promotion. Come if you want to know more about how to use dragons. I'm not going to show how to reduce data because we have so many instruments, it cannot really be done, but how to customize the dragons. It's a pipeline, it can be run automated, but we are scientists too. We like to tweak and optimize our reductions. So I'll show you a few tricks on how to customize your reduction. And that's what I have. I'm ready to take questions now.
That's great. Thank you, Kathleen. Great to see all the progress. Let's see, we do have a couple of questions in Whova. The first one is, how is Dragons related to packages in the AstroPi ecosystem? Is there a possibility of using Dragons for non-Gemini instruments? So
we use AstroPi heavily. Dragons is a collection of various packages. One is AstroData, which is completely generic. It's not Gemini related. To make it work with Gemini, you have to add another package that provides the layer, basically the translation between, oh, here's Gemini data, here Astro data, how you recognize Gemini data. So in that sense, yes, it is possible to plug in non-Gemini instruments. And in fact, we've done that for SOAR, for example. I can't remember the name of the instrument, but we did play with that. The integration for other instruments at this point, it might be a tiny bit clunky because we're really pushing on supporting our instruments. But intrinsically, the hooks are in there to be used for other instruments. But it does require the person to actually write the layer that will make the system recognize as this or that instrument.
Thanks. The next question, what magnitude will the quick look spectral reduction work well to? In other words, will it work well for fainter targets where you would generally need to tweak the reduction?
Well, that's somewhat part of our science verification that we're about to start, trying to answer questions like this, try to figure out what the limits are. From my current testing, I've seen it work on fairly faint stuff. You look and say, yeah, I think there's a line there, and it will find it. So how automatic it will be, that's to come. That's part of the work that is ahead of us in the next year, trying to figure out what the limits are.
Great, thank you. And then, let's see, everything flipped around on me. There we go. One more question here. What are the chief differences between the quick look and science quality versions of Dragons for long slit data reduction?
From the top of my head, there's the cosmic ray rejection. And frankly, if you're using the Yamamatsu and you have a fairly long exposure, it shows. It's a big difference. So we really want, for the science quality, we really need the cosmic ray detection. And then the slit function, this is something that we've always sort of wanted in Gemini RF and was never implemented. It was implemented, but never released, so we never managed to finish this one. So that would be nice. We've had report people say, oh yes, we'd really like to have that. So that's another improvement. And from my point of view, it's the interactive tools that really do make a big difference. I found, well, in Gemini RF, I always tell people, always run GS wavelength interactively because it fails in half the time. Well, at least in Dragons, wavelength calibration, you'll probably never have to run it interactively. It is very, very solid. One thing that I found I like to do interactively is fitting the sensitivity function, my spectrophotometric star. because it works just as well as with RF, but with the interactive tool, you can really tweak it and get something much bigger, a bit better. So that's one that I found some really good values in doing it interactively. So yeah, I think that's mostly that. And fundamentally, we will spend months checking the science quality of the output. And I think that's what gets the stamp science quality from our point of view.
That's great. Thank you. I see we're at the end of time now. We're going to take a 10-minute break now before we come back with a sequence of 3 talks about future adaptive optics systems. I do see there was at least one more question on the Dragon session in the Q&A, so please go ahead and continue having discussion in that Q&A area following this session. Thank you, everyone, and we'll see you back in 10 minutes after a short break. Thank you. We'll get started again here in just a moment. All right, welcome back, everyone. Now we will have the first of 3 talks today about future adaptive optics projects at Gemini. Recall that earlier this week we heard about GPI-2 that will come to Gemini North as another adaptive optics development improvement in the near future for Gemini. First, we will hear from Gaetano Sivo, who at Gemini is the principal investigator of the Gemini North Adaptive Optics Project, regarding GNAO's progress in recent times and where it is headed in the near future. Gaetano, if you're able to share your screen, and I see you and see that you're unmuted, so perfect. Once you get your screen shared, please proceed.
Yes, thank you. So let me go back to slide 1 slideshow from start. Okay, so can you see it well?
I see your title slide. Perfect. Thank you.
Thank you. So I will start off. So hello everybody, and as Henry introduced, I will present the status of GNAO, that is our workhorse facility that we are currently designing and developing for Gemini North. Here, so the outline of this talk is I will present what GNAO is in that stands for Gemini North Adaptive Optics in a nutshell, and then introduce the science capabilities of this facility and present one science case example that we have developed with the science team. And then later, just after me, Suresh Sivananthan will actually present much deeper science case example that we can have once we couple a science instrument at the back end of this facility. And finally, give a few words of the system architecture that we are currently proposing. And to remind everybody, GNAO is a project that is currently within the GEMA award funded from the NSF. So the goals for GNAO is, so first, to revitalize the aging AO facility that we have at Gemini North, Altair. Use one of the world best sites, arguably, for adaptive optics, that is Mcconaughey. And we want to support nightly queue operations using adaptive optics, meaning that on any given night that the conditions are allowed to do so, we'd like to use AO. And finally, also to support Gyrmos, that is a Canadian-built TMT Pathfinder instrument that you will have a presentation in a few minutes, and enable a path for adaptive secondary mirror facility also at Gemini North. That will be the last of the 3 AO talks that we'll have today by Paul Hurst. And we will be building this facility upon the legacy that we have acquired through GEMS along the past years. So scientifically, we want to support high spatial resolution, wide field near-infrared adaptive optics imaging and spectroscopy for multi-messenger and time domain astronomy, and also cosmology, stellar population, and the wide diverse science cases that we have been developing also in the era of James Webb and Rubin operation coming along. GNAO will have two principal AO modes available, and here I will briefly present the difference between the two. So we'll have on the right-hand side what we will call the wide field mode correction that GNAO will provide. So meaning that we will have access to the full AO technical field of view to acquire the guide stars. And what we will be doing is simply measuring the wavefront. And as you can see, you do not sense the entire volume of the telescope. This is why you get what we can call a good but still moderate and modest correction. But if you put the laser guide stars, and that's what you can see on the left-hand side, narrower together, then you start to sense the entire volume that you have above your telescope. And that allows you to sense the entire volume of turbulence and determine the correction that you'd like to apply to using the deformable mirror and get the correction that you want. And that's what we would call the narrow field mode in the case of GNAO, providing a laser tomography adaptive optics correction. So in a nutshell, GNAO, as I said, will have those two different modes, GLAO for the wide field and LTAO for the narrow field at Gemini North. It is strictly designed to currently feed imaging and spectroscopic instrument, and principally thinking of what I will call here the visiting/facility instrument GEARMOS, including an imager. But also we could think of using, because we can enable the capability of the GMOS red end part of the instrument, and use the near-infrared imager that we have in the SARS GSOI if needed. GNAO needs to deliver a wide field correction, as I said, using GLAO over the full 2 arc-minute AO technical field of view, and that is mostly for GEARMOS IFUs science, including the AMO-AO correction when needed, and imaging science cases using the large field of view available, that is here about 85 by 85 arc-second square. The second mode is that it needs to deliver, as I said, a narrow field correction provided by an LTO correction in an area of about 20 arc-second squared in the near-infrared, and that is to field the tiled IFU mode of GEARMOS that you can bring all 4 IFUs together to the center, and some high performance narrow field imaging within the LTAO area of a 20 by 20 arc-second square. And finally, as I said, all the developments currently being done is also to keep open future upgrade to the telescope that could be, for example, used with an adaptive secondary mirror on the current GLAO feasibility study. Where is GNAO in the current landscape? So on this plot, I did put only in the near infrared the different facilities that we have all around the world. And the main message that I would like to highlight here is that on the narrow field science that we will be able to achieve is that we will bring Gemini up to the standard state-of-the-art narrow field AO performance that we can get on an 8-meter telescope. And on the wide field area, because GNAO will be working on a 2 arc-minute field of view, so that's wide field, but still narrow enough in terms of AO when you have multi-laser systems. And thanks to the great conditions that we will have on Mauna Kea, the wide field mode of GNAO will be performing as good as what currently GEMS is capable of doing, but but once we add the MOAO corrections provided by GEARMOS on the IFUs, we will have unique high corrections on those field of regards of the 4 IFU. The science capabilities for GNAO. So as I said, we have developed the science cases, and mostly they are driven by the GEARMOS development that will be presented later, and with focusing on the GEARMOS spectroscopy and the GEARMOS imaging science cases. So that has been driving GNAO. And as I said, we can enable also some optical capabilities via the red end part of GEMOS. So the entire science cases part of GNAO has been developed both in conjunction within Gemini NOIRLab, but also with astronomers and scientists within the Gemini community and a partnership. So you can have here the list of the people that have been involved, but the list is not locked down at all. We are still recruiting, and if anyone is interested in joining the team and help the effort in developing this, please do not hesitate to contact us. And for example, we have members from almost all the partners of the Gemini partnerships, except currently Argentina and Brazil. And I am sure within the call we have some Argentinian and Brazilian scientists. So if you are interested, we would be very happy to work with you all. So GEARMOS, just in one slide, because Suresh will present the entire instrument in much more detail, is an AO-fed multi-object integral field spectrograph that also has an imager, and GEARMOS will be able to observe 4 objects spectroscopically at the same times. On top of it, each IFU will have on top an MOAO capability to improve the performance over the corrected field. And as I said, Guillermo's will have a near-infrared imager embedded into the instrument. So this instrument is really very well suited to address the majority of the GNAO science cases that we have been proposing. So where is GNAO currently versus with what we currently have at Gemini, both North and South, Altair and GEMS? So I would say that in summary, I will not go into the details of all those numbers, but in summary for the requirements, GNAO will be able to do as good as GEMS in terms of performance, and as easy to use as currently what Altair is. So it's a very good compromise. And then there is the narrow field mode that we have with LTEO that brings actually also an even higher level of performance. About the same level of sky coverage as GEMS, and as I said, very easy to use as well what Altair is with the current two nighttime staff that is currently needed to operate the telescope and the instrument. A better, one deeper look at the image quality requirement that we have, because that's what gives usually the idea of the capability of the instrument. So we have on the top side of this chart the performance that we will be able to achieve in wide field mode, so about 120 miles in K-band for the entire sky coverage that we're aiming, that is about 60% at the galactic pole. And in narrow field mode, we will have performance close to currently what GEMS is capable of doing in the very faint areas, and as good as any other or classical narrow field science, narrow field AO instruments are currently capable of developing. So the science cases, as I said, so for both, first for imaging, so with either wide or narrow field mode, we have high resolution imaging of solar system objects. So for example, monitoring the giant planets and their satellites, multiplicity and surface properties of icy small solar system bodies. The main point for Gemma and GNAO here per se is to also enable rapid response to transient events using AO, so to follow gamma ray burst, transient events in the area of Robin, and solar system transient events. And finally, high resolution imaging of nuclear star clusters that are very crowded fields. So having a good AO system here to resolve is important. So a flexible queue scheduling and simplified operation will enable AO-assisted time domain astronomy. Another example, in this case, here you're looking at a science case needed that do require narrow field AO science. So here, when we look at intermediate mass black holes, we know that they're missing link between stellar and supermassive black holes. So if you look at globular star clusters here, for example, we have many of them distributed around the galactic center, and such a survey is ideal for GEMOS because they're crowded targets and they're dusty. So you need infrared and you need AO. The massive bulge is have the intermassive black hole sphere of influence of about 3 arcseconds, so it will fit very well in the area, and this type of targets do fit well the Guillermo's call. Sorry, I missed it there. So in terms of the configuration, so to give simple numbers, so GNAO will be fed by two sodium star laser developed by manufactured by Optical. Each laser will be split in two to feed and will then be feed each their own LLT to create the 4 laser guide star constellation on sky. The AO bench will then use those 4 laser guide star to feed the 4 laser guide star wavefront sensor adapted to the constellation that is needed for either wide field or narrow field mode. We will have one deformable mirror to apply the correction, and as little but effective optics as possible to increase reliability and especially throughput. I will skip this part due to lack of time. It's just the system architecture of the facility. So maybe here just to mention that we have those subsystems that are part of Genio. So we have the laser gas star facility that takes into account laser and laser launch telescope and beam transfer optic. The system controller that connects all the parts together, the AO bench, that is the optomechanical part of the instrument, the real-time computer, and finally Gearmos that is not within Genio, but still is the main facility instrument that we'll be using. So I'll skip this. Where we are currently, so we have the adaptive optics bench request for proposal that is planned to be released at the end of September. It will be a two-phase procurement. So the phase A is currently planned to start around May of 2022. It will be a competitive phase to reach conceptual design, and then a down select to one single vendor to start phase B, that is from preliminary design down to first light, about 1 year after. In terms of the different work packages, the laser launch telescope are moving toward critical design. The LGSF and the RTC are both currently moving toward building. And in terms of timeline, we're aiming currently first light for Genio in the fiscal year 2028. So in conclusion, Genio, we have made significant progress since the conceptual design review. The RTC, laser launch telescope, the Toptica laser are all secured procurement. We have developed science cases, scope, requirement, concept of operation. Everything has been fleshed out and signed off for the Genio facility as a whole. And we do strongly believe that having a Genio and a flexible, versatile Genio LTE system on Mauna Kea will allow us to meet the performance needs that we have to feed Gearmos, both for spectroscopy and imaging. Thank you.
Thanks, Gaetano. That's excellent. Let's see. I don't see any questions in the chat.
Check.
Yeah, I'm not seeing any there right now. So do you have a personal favorite among the science cases that you're most excited to see us accomplish with this?
Me, yes, I'd say, but mostly because I'm also coming from GEM, so I do like very crowded field, and so when we look at globular clusters, so that may be one of the reasons I did show this example. I think it would be good to show that we can, as I said, we can reach the same performance level as GEMS, but with an easier system to use, we can get a better accuracy, and that would be an interesting result to obtain. But then anything, as I said, we have a long list of different flavors of science we can do, and I am sure the entire community would find its interest.
Yes. Excellent. Well, if anybody thinks of a question, please feel free to enter it in the chat. Gaetano,
yes,
and others can address it later after the session and continue the conversation there. So thank you, Gaetano. If you could, yep, you're unsharing. Sure. Thank you. And Suresh, if you're ready, you could turn on your video and unmute and share your slides. In our second adaptive optics talk today, Suresh Sivandam of the University of Toronto will tell us about the Gearmos instrument project that will work with GNAO to provide some spectacular new capabilities to the Gemini user community. And let's see, Suresh, I see your title slide in presentation mode, so that's perfect. And when you're ready, you can, if you're unmuted, you can proceed, please.
Sure, thank you for that introduction, Henry, and hopefully you can hear me.
Yes, loud and clear, thank you.
Perfect. And I wanted to thank Gemini for giving me this opportunity to give this talk about an exciting new instrument capability. And I also wanted to thank Gaetano to set up my talk as I come in here. And so what I'm going to talk about is the Gemini Infrared Multi-Object Spectrograph. We've heard the name GearMOS several times, and give you an overview of what this instrument is and where we're at and what are the science cases that we're trying to tackle. And this is mainly being developed by a consortium of Canadian universities and the National Research Council of Canada. And there was a nice presentation earlier about the GHOST instrument, and there are colleagues working on this instrument. And it's actually a fairly complex instrument with many moving parts. There's an adaptive optics component, there's a spectrographic component, and all of the supporting hardware, as well as the imager, and it's a highly cross-collaborative project. And of course, our Gemini is a significant partner in this project, and are contributing staff and some resources to make this instrument a success, and we thank them for that. And of course, GearMOS, I think was mentioned by Scott earlier in the week, is kind of a transitional instrument. It's somewhere between a visitor instrument and a facility instrument, with the goal of becoming a facility instrument at the end of the day when it is actually commissioned at the observatory. So what is GearMOS in a nutshell? The project has gone through some evolution, and when we came up with this idea, the Gemini North AO facility did not exist, and we had GEMS, and the goal we wanted to do is develop a Pathfinder instrument with full scientific capability that did multi-object integral field spectroscopy. And this would be an instrument that would then get developed in the future and become a TMT instrument that would operate behind the TMT AO system, Nefarious. So we started off with that, and there's been quite a bit of evolution in the project. And as you know, the Gemini North AO facility has been funded. It's on a better site, much more modern system, offers Q observing, and it became a no-brainer decision. Especially, you'll see the main science cases for GearMOS are related to survey science, to baseline our instrument behind GNAO. And so we have done that. That's been the biggest evolution in the project. And I think it's a mutually beneficial evolutionary direction, because GNAO requires a great facility class instrument, and GearMOS will be able to fulfill that role. So what is GearMOS in short? It has basically two scientific instruments. One is a multi-object integral field spectrograph, that's shown on the right here, where you have up to 4 spectrographs that you can select any object within the Gemini AO field and do spectroscopy, and I'll go into the details in a second. And then there's a parallel imager. So you could either do imaging or spectroscopy, depending on what your science case is. And if you're willing to take some vignetting from the pickup system, you can do both spectroscopy and imaging at the same time, because they both simultaneously look at the field from the AO system. So in terms of science drivers, we developed this instrument considering it as a general purpose facility class instrument. So there's a broad set of science cases that our science team has developed. Most of them are highly focused on spectroscopy, because that's what we think will be scientifically very compelling in the next decade. And so we have a broad set of science cases ranging all the way from star formation within our Milky Way, all the way to reionization in the early universe. And one of the key aspects of this instrument is also being able to do James Webb follow-up, doing the very long exposure type integral field spectroscopy that you wouldn't have time to do on James Webb. So our science team, which has also gone through some evolution, we have our original science team within the Canadian community and some international experts. Now we are we're in the process of consolidating the science cases between what the GNAO science team has already developed for their facility, as well as the GearMoss science cases, though there's already some overlap between the two and some feedback between the two prior to this consolidation, which Gaetano pointed out. And these are some of the key science cases that we've developed in detail as part of our science document, ranging from galactic to nearby galaxy science to extragalactic science cases. Now, when you design an instrument, especially a general purpose one, you want to pick a few key science cases that would assist in helping you develop requirements for the instrument. And so we made an executive decision on 2 different science cases that exercise different aspects of GearMoss, and one of which, and this is truly what GearMoss was originally envisioned for, is to do a high angular resolution, high redshift galaxy survey to complement a lot of the work that's being done with local galaxies with integral field surveys in the optical, like Manga, SAMI, and various others that have done so in recent times. And the goal here is to be able to probe galaxies down to kiloparsec scales, so you can do the similar kind of science that's being done in local galaxy surveys and try and understand galaxy formation and evolution processes. This is hard to do, and I'll just show you a slide in a second. There aren't a lot of surveys of high redshift galaxies with significant number of galaxies observed at high angular resolution down to this level. And there are a number of reasons for that. These objects are faint, so multiplexing is absolutely key. AO systems are finicky, so it's, and depending on condition, etc., it's hard to always get consistent data. And so we're attempting to address all of this with GearMoss, with the multiplexing and the union with the Gemini North AO system, which is supposed to be state of the art, and of course the great site up at Mauna Kea. And so a lot of our science requirements are driven by a reference galaxy survey that the science team has put together. And this will attempt to optimize both observing efficiency, sensitivity, and basically overall performance of the system. So looking at everything that will impact a survey. So just for a reference to show you the state of the art in high redshift galaxy surveys, integral field surveys, is probably the Z-SIM survey that only really has about 40 galaxies or so observed at high angular resolution because of all of these challenges. And our present plan is to be able to boost the sample size by at least a factor of 10 and even more, and by both increasing the efficiency of the survey speed, and also the sensitivity of the instrument and the quality of AO correction. So the other science case, reference science case that's driving the instrument design is the narrow field mode, which is typically used by the nearby galactic and nearby galaxy science programs, and Gaetano talked a lot about that. And one of the key things is looking at the chemodynamics of globular clusters in the galactic plane and bulge, and this requires exquisite image quality and the central regions of these clusters, and also high moderate spectral resolution, so you can actually resolve the kinematics of these objects. So the goal of these 2 science cases is to basically exercise the full parameter space of what GearMoss can do. So in the end, what are the requested instrument modes? Well, we have basically 2 modes. One is multiple objects, and for this, we have to do our own AO correction in addition to what GNAO will provide. And this is what we call multi-object AO, and I'll explain that in a second. And then the other mode is basically a single object or narrow field mode, where all of the integral field spectrographs are put together in a closest packed arrangement. There's some gaps but they're all fairly closely packed. And we would use the high angular, the laser tomographic AO correction from the Gemini AO system, and basically slave our AO system from doing anything. And just a little bit of a description of what multi-object adaptive optics is. I'm sure you remember Gaetano's figure of what GNAO does. And obviously it does the first layer of correction, and we use the ground layer AO correction. And our spectrographs have their own deformable mirrors to correct along the specific line of sight of our target to get a significant improvement on image quality. We use the information that GNAO is providing to us to calculate what's the optimal correction. And just some metrics here. These are simulations that we've done, and we're basically trying to optimize the encircled energy within 100 milliarcseconds, as that's the spatial scale that we care about for these high redshift galaxies. And our AO system can provide, approximately 60%. Our target is 50%. Obviously, there's some contingency there, but our simulations show that this is a viable plan. And this has heritage. Our team has actually demonstrated a multi-object AO system on Sky on Subaru, and we also have a test bed that's now operational. That's trying to do AO risk retirement. And of course, we actually have peer review as part of the preliminary design of the AO system this week, and we'll be getting very useful feedback on that. So in the end, after all of the science cases and discussions with the science team, we've come up with a set of requirements for the instrument. And so the top 2/3 of the requirements are for the spectrograph. We have 2 spectral modes, RF3000, RF8000, and 3 spatial modes. So very small IFU fields, about an arcsecond, all the way up to pretty coarse fields, about 4 arcsecond. And we'll have a corresponding increase on your sampling on the field of the instrument, of the IFU. And we have an imager that's approximately in 1.5 arc minutes on the side, and it's designed to Nyquist sample at H band and the usual near infrared wavelength range. So if you want more information about the instrument, there's a recent SPIE paper that you can look up with all of the parameters discussed in detail. And of course, I think Gaetano mentioned this, and also Kathleen mentioned it, we're using image slicers to get the best low surface brightness performance. Just very quickly, what does the architecture of the instrument look like? We have our Gemini North AO system here, and GearMOS has multiple optical systems that allow you to pick off the sources in the appropriate location and feed the AO system that each spectrograph has. And that goes into a big cryostat with 4 infrared spectrographs and the imager. And of course, we're constantly communicating with the Gemini North AO system to get the most up-to-date information about the atmosphere and their correction in order to get the optimal MOAO correction for our instrument. So we're actually pretty far along in our instrument design. We're in the preliminary design phase, the latter bits of it. And this is how our instrument looks like. It looks like a standard Gemini instrument, a little T-shaped instrument. But we have 2 major optical components in addition to the calibration system that does spectral calibration and flat fielding, et cetera, which is all built in. And we have our pickoff system here and our AO system that does the correction, which gets fed into this big cryostat, which holds all of our spectroscopic and imaging components. And you can kind of see an internal view of that over here. And I'll show you one other image that gives you a better idea. Just so you have a sense of how it works, when the light comes in from GNAO, it comes to a focal plane. that's located at the very center. And we have these R theta pickoff mechanisms that we can position anywhere within the 2 arc-minute field of view offered by GNAO and send the light into our AO system, a deformable mirror. And each of the 4 spectrographs have a corresponding AO system and a pickoff system and like service system. This is a quick internal view of the cryostat, and we basically have a square tube here, which consists of all of, each side has a spectrograph, and at the very center, we have the imager that accesses the full field. So with that, I wanted to end a whirlwind tour of what GearMOS is, and I think it's we have a great partnership with Gemini, and having access to GNAO is going to be a game changer and really give the necessary performance we need to do the science that we require. Right now, I said we're in PDR. We're expected to pass that phase, preliminary design phase. We're expected to pass that phase early next year, and then we're planning on commissioning a commissioning plan that coincides with when GNAO expects first light. Thank you very much. And of course, I'm available for the chat session tonight, or this afternoon, or whatever time zone you're in, and tomorrow before the start of the conference. Thank you.
Thanks, Suresh. Excellent talk, and good to see all the progress being made. Let's see, I don't see any questions in the chat right now. If someone has additional science they're interested in doing with it that, wouldn't tweak the design, but just to add in, who should they get in touch with?
Just get in touch with me, and I'll put you in touch with our project scientist. And the other option is, and I guess this is where we're trying to figure out what's the best way to consolidate the different science inputs. If there's one set of inputs going to GNAO and the science team there, and then there's another set of inputs going to GearMOS. But I'm on both science teams, so please contact me, and I will talk to you, and then we can figure out what's the best approach.
Great. Oh, let's see. I do have a question in the chat now of reminding us of when you said first light would be. That coincides with GNAO. Right.
So I think Gaetano mentioned first light is meant to be in fiscal year 2028, I believe, in his presentation. So that's what we're aiming towards.
Yeah.
Each system will not really function without the other. So I think we're joined at the hip here in terms of development.
Absolutely. Absolutely. Great. Well, thank you very much, Suresh. And people should continue any conversations in the chat there, and then sign up also for chat with Suresh during the upcoming chat sessions. Paul, I see your video and that you're unmuted. Perfect. If you could share your slides.
How's that? Is that coming through?
Great. Yes, it is. And it looks like you're in presentation mode. So perfect. Give me 1 second I'm on a small screen today. So great, thank you. So we're a minute or so ahead of schedule here, so we can get started in just a moment with our final adaptive optics talk today, where Gemini's Paul Hurst will discuss the ground layer adaptive optics feasibility study that we recently conducted for Gemini North. And I think, Paul, you could go ahead and start now. We're only just a few seconds ahead of schedule at this point. Perfect. Thanks.
Cool. Thanks a lot, Henry. Yeah, so as Henry just mentioned, I'm going to tell you about this ground layer AO feasibility study. I'm presenting on behalf of a fairly large team of people at Gemini who have been involved in this. I've got the list of names up on the screen there. So thanks to all my teammates on this. So ground layer AO, I think people are probably familiar, but just as a quick reminder, the baseline here is that we only attempt to correct the ground layer turbulence, so the turbulence in the atmosphere just above the telescope. We ignore all the turbulence at high altitude, and that gives us a lower fidelity correction. The baseline we're looking at for a system like this is a factor of 2 smaller point spread function than natural seeing, but a large field of view. So the design we're looking at here would support the entire GMOS imaging field of view, for example. The idea we're looking at is to use an adaptive secondary mirror, as has been mentioned, and to use the laser guide star facility from the GNAO project that Gaetano just mentioned, which gives us 4 10-watt sodium sideward LGS beams. For the NGS side, the tip tilt and slow focus, the concept we're looking at is to use P2WIFS, or the OI on instrument wavefront sensors. We may need to do some upgrades to do that to those to get the kind of performance we need. I'll come back to that in the talk. So adaptive secondary mirrors, what's the deal here then? So the idea is that the secondary mirror of the telescope becomes the deformable mirror for your adaptive optic system. There's essentially 2 vendors of these right now, Adoptica, who you can see one of their mirrors on the left here, and Tno, you can see one of their mirror designs on the right. The principle to first order is very similar. There's a thin face sheet, they call it, which is a piece of glass, a couple of millimeters thick, so it's very thin, silvered on one side. We will silver it we will coat it in our regular coating chamber that becomes the front surface, a reflecting element of the mirror. And then you have a number of actuators where we'd be looking at, we don't have an exact number, but of order of magnitude 1,000 actuators or slightly less. But you have all these actuators that push and pull on the back surface of that piece of glass in order to bend the glass, and that makes it your deformable mirror. The Adoptica design uses a magnetic voice coil arrangement. So you have all these little magnets glued to the back of the glass face sheet. And then the actuators have voice coils, which are little, copper solenoids, which push and pull on those magnets to bend the glass. The Tno design is actually quite different. The actuators are these little yellow cylinders down here. These work on a magnetic reluctance principle, and they have a physical push rod up to the back of the mirror. The 2 different technologies both have very different pros and cons. They both have their strengths, they both have their challenges, but there are two potential vendors out there. So why would we want to do GLO with an ASM? So as I mentioned earlier, the baseline is a factor of 2 improvement in image quality. So your regular kind of common or garden 0.6 arc seconds natural seeing becomes 0.3 arc seconds with GLO, which I think you'll all agree is pretty good. This benefits both angular resolution, obviously if you're trying to resolve structure in sources, but also if you're just looking at point sources, especially in the infrared, you get a huge sensitivity improvement simply because you can use a smaller aperture because the point spread function is smaller. So you get less skylight in the aperture and therefore less noise. The arrangement we're looking at has no throughput or emissivity penalty. So the throughput of the AO system, if you like, is 100% and the emissivity is 0%. Because there's no AO bench in the system, there is no additional optics in the science path. We simply replace the regular mirror with an adaptive secondary. And we don't take up an instrument port, and we can feed light to any of the instrument ports. So it really does become part of the telescope. And you could imagine a future where using GLIO becomes the default, just like we use tip tilt guiding currently. Nobody thinks about observing without tip tilt guiding or active optics on Gemini. And we could envisage where GLIO becomes similar, and who doesn't want better seeing? Now, there is a big caveat here. We do need the laser guide stars, and we can only propagate the lasers when the skies are clear. So that is the main limitation. We just did a user survey targeted to people with who've had similar kind of science cases or proposals before, and we've been reviewing some science cases from existing work. And many thanks to those of you who responded to the user survey. It shows very strong support for the concept with a wide range of science cases, which is really good to see, really gratifying. So why are we doing this feasibility study now? So we actually considered GLIO in the original concept for what became GEMMA and GNAO. And it became apparent during that there's some pretty big unknowns. We didn't really have a design of how we could implement this on the telescope. We had some kind of ideas, but no more than that. And the cost was really unconstrained. We really didn't have a good grip on how much it would cost. And of course, it's difficult to write a proposal on that basis. So it was descoped out of GEMMA GNAO because of that. And the solution, the way forward, of course, is to carry out this feasibility study to figure out if we do have a viable way to put this on the telescope and to get some idea of the cost. And if we can do that, then we're well placed to respond to subsequent funding opportunities. So the challenges, why is this so difficult then? So in my view, there's two real challenges here. The first is kind of obvious. Can we procure a suitable adaptive secondary mirror and mount it in place of the current M2? Now, we have to remember it needs to be able to maintain all the functionality of the current secondary mirror system. So tip, tilt, focus, all that kind of stuff, we need it to do as well. There are quite a few operational challenges associated with ASMs. I don't have to go into details, but there are some ASMs out on other telescopes, and the technology is improving, but there are challenges there. The real difficult question, on the ASMs, as I mentioned, there are vendors that can design and build ASMs for us, so it's doable. The real difficult question is, where do we put the wavefront sensors, specifically the laser guide star wavefront sensors? So the acquisition and guiding unit on Gemini is really very space constrained. Let me just skip on to this next slide. This is the cartoon off the website of the ANG. So as a reminder, the ANG sits in the center of the instrument cluster on the back of the telescope. And it has the peripheral wavefront sensors, acquisition cameras, and the science fold, which directs the light out to whichever instrument port you're using. Now, earlier concepts for GLAO on Gemini envisaged the kind of somewhat obvious arrangement where you replace the science fold mirror. Right now, it's a fully reflective mirror. If you replace that with a dichroic mirror, so you transmit the visible light straight down to a set of upward-looking visible light wavefront sensors, and you send the infrared light out to the 4 science ports. That's all good, but sounds good, but there's a problem with that. And the science fold is actually quite big. And right now, it being a fully reflective mirror, it has a metal structure behind it which supports it and holds it flat. As the telescope tips around the sky, the science fold goes through almost every possible orientation, depending on which instrument you're using and this kind of thing. And it turns out if you want to, well, if you want to have a dichroic science fold, you can only support it around the edges. You can't have a metal lattice behind it because some of the light is going straight through. And if you have such a large piece of glass only supporting it around the edges, as you tip the telescope around the sky, it sags under its own weight due to gravity, too much to keep it flat within AO tolerances. So you lose optical quality because of that. So that doesn't work. So we're looking at other ways to do this. If we can't separate the LGS and the science light with a dichroic, maybe we can separate them spatially. So you look at the ANG stack here. So module 3, for example, this is where P2 WFS sits. I should have just mentioned, it's maybe not obvious. When the system's assembled, these units kind of fit inside each other. It's a kind of concentric rings that's, the science fault slides up inside module 3, for example. So you look at this and you think, well, there's some empty space on module 3 here. Maybe that would work. Well, over on the right here, this is a photo of the actual module 3, and you can see there really is no extra space on there. So it really is very space constrained in there. So let's have a look at the way light passes through the telescope then, thinking about a science beam and a guide star beam. So the diagram on the left is a kind of schematic view of the center of the telescope. The blue line in the middle represents the primary mirror. This kind of truncated cone at the top, this is the M1 baffle, the black tube which sticks up from the center of the primary mirror. You see in photos of the telescope. And then underneath we've got the ISS and the ANG. And the beams I've shown here, the green lines denote a science beam at the edge of the GMOS science field of view, the GMOS imaging field of view. And the yellow lines denote light from a laser guide star. So these both come from the secondary mirror up at off the top of the screen and come down to focus at the back of the telescope here. So you'll notice that the laser guide star light comes to focus significantly behind the science focal plane. And that's because the lasers illuminate the ionosphere. There's a layer in the ionosphere with sodium ions, about 90 kilometers. So the LGS light doesn't actually come from infinity optically like the science light does. And the result of that is that it comes to focus behind the science focal plane. The other effect of that is that as you go up the telescope, the LGS beam is actually wider than the science beam because it's not coming to focus as quickly. So we have these two beams and we're looking at separating them spatially. So obviously they overlap completely at the secondary mirror because the secondary mirror defines the pupil of the telescope. And at the focal plane, they're completely separate. So there's a point in the middle that we've labeled this beam separation point. And that's basically the point where the two beams don't overlap anymore. You can imagine if you make the science field smaller, if you move the green beam to the right, then that point moves higher up in the structure. Likewise, if you make the LGS asterism larger, if you move the yellow beam out to the left, then you get the same effect, that point zips upwards in the structure, which is great because the higher up in the structure that is, the easier it is to separate these two beams. But there's a catch. If you move the LGS beam too much to the left, then it starts to vignette on the M1 baffle, as I'm showing in the middle picture here. We don't want to change this baffle because it's there for a reason, providing optical baffling on the telescope. But we do get this slight vignetting of the M1 of the LGS beam on that baffle, which I'll come back to discuss later. So looking at this beam separation point, I've got a plot here showing on the y-axis the height of the beam separation point up the telescope, the distance from the focal plane. So basically how high in the structure the beams separate. And on the x-axis, I've got the LGS asterism size. So you can see as we make the different colored lines then represent different science fields of view. So you can see as we make the asterism larger, as we go to the right, then the beam separation point moves up through the structure. And as we make the science field larger, then the beam separation point moves down in the structure, hovering between these lines. And on the y-axis, these dashed lines represent some of the crucial parts of the A&G structure. So P1 WFS, the P1 rotary table, P2 WFS, the P2 rotary table, and the science fold. So we'll come back to that point, that plot in a second, but you can see from this, we want to go to the right on this as a big driver because the bigger asterism gives us higher up in the structure for a given field of view. But if we go too far to the right, if we make that asterism larger, we hit this LGS vignetting issue that I just mentioned. So the question is this a problem? Well, it depends how big you make it. So if we look at this plot on this diagram on the left, so what these diagrams are showing, this is the pupil of the telescope, if you like, as seen at the wavefront sensor. And the different colored lines drawn on here represent the areas which will be illuminated by the 4 different laser guide stars. So we would have 4 laser guide stars, 4 laser wavefront sensors, 1 on each of the guide stars, and they're in a square around the telescope. So the vignetting from on each of these would be kind of at a different quadrant of the pupil, if you like. So the area in the center here, the vast majority of the area is covered by all 4 laser guide star wavefront sensors just fine. It's just that each of the wavefront sensors has one of these little crescents around the edge, which would not have any light coming through to it and would give us no measurements of the wavefront. Now, if you make the LGS asterism even bigger, what happens is these crescents start to overlap. So in the center image, you can see they're just kind of touching, but over on the right, if you go to a really big asterism, you've got these fairly big divots, which are vignetted on 2 of the 4 wavefront sensors. So essentially, we had a bit of a hypothesis that for GLAO, if every point on the pupil is covered by at least 3 of the wavefront sensors, that seems kind of viable. As a reminder, most of the pupil is covered by 4, but there are these crescents where there's only 3. So what we did some fairly simple AO simulations of a GLAO system with this, thanks, I see the stars there, with this vignetting of the LGS light. And we've got some delay, here we go. So this is what we've got. So the purple line is natural seeing, the open loop line is natural seeing, the red line is the closed loop, the GLAO system, and you can see the model reproduces pretty well this factor of 2 in image quality that we sort of stereotypically expect for GLAO. So we're coming from, the 0.5 comes down to the sort of 0.25 region and so on. Now, just to stress, this model was specifically to investigate this vignetting issue. There are probably a lot of effects in the actual system which are not modeled in this model. So the simulation is probably very optimistic where you see it getting close to the diffraction limit. There's undoubtedly other things in there which will degrade the performance. But the point being that we confirmed that if we have these little crescents vignetting on the LGS, as long as they don't overlap, then the AO performance seems good. So we can mark this back on the plot that I showed earlier. So this is the same plot with some extra stuff overlaid. So if we make the LGS asterism too large over on the right, we're going into this red area, and we're losing AO performance because of the LGS vignetting. If we try and go too far down in this plot, if we try to separate the beams at the science fold level, for example, we really don't see any way mechanically to do that. So what I've labeled as increased A and G complexity is really kind of impossible design. But also the other driver, of course, is we want as large as possible science field of view. So that points us to this area with the green dashes around it here, nestled in this little corner, which looks quite optimistic because this is the 6 arc-minute science field of view. So we're about the size of the GMOS field. And it suggests to us that we should be looking at picking off the light round about the P1 level, where the beams will separate, and that looks a viable design. So the question is, can we find a way to do that? Well, actually, yes, we can. So it just so happens that there are some holes in the sides of the A and G, the acquisition and guiding shell, that lead to available space volumes in the mirror cell. Honestly, I'm not sure what the original idea was for these holes, but there are these holes that lead from the A and G into the mirror cell. So the concept we have is to insert these deployable LGS pickoff mirrors into the beam. They'll swing down from above the P1 level to be in the beam around about the P1 WFS level, bounce the light back up and out of these holes in the side of the A and G. You can either go out the other side, or the way it's drawn here, you could actually, there's an alternate design which bounces the light across to the other side. Either way works. And then we can locate the actual wavefront sensor optics and the detector and all that kind of stuff way out here in the mirror cell, out of the way of everything else. Here's some 3D renderings showing what that would look like. I'm not going to go into details on these, but it looks like we have a viable way forward. So there are some open questions, though, specifically with regards to the natural guide star wavefront sensing, which we need for tip tilt and slow focus with an LGS system. So the baseline idea we have in mind is to use P2 or OI for this, just like we do for natural seeing right now. The question is, are they sufficiently fast and sensitive to give good sky coverage? So we haven't done the simulations yet to figure out how fast we need to do NGS tilt. That will tell us how bright the guide stars need to be. There's some other complications. The LGS pickoff mirrors will vignette the P2 and OI patrol fields somewhat. So the area of sky available to the guiders will be smaller. And the LGS asterism, and thus the pickoff mirrors, are fixed relative to the telescope. They don't track on the sky. So stars, NGS stars, will rotate round through that vignetting pattern through the gaps. So we would need some software handling of that. Now, the observatory is investigating upgrades to P2 and OI anyway. We just don't know yet, but it could be that these upgrades become prerequisites for doing GLAO. Basically, if we get higher sensitivity on those wavefront sensors, we can guide equally fast on fainter stars, and that will recover the sky coverage for us. So in summary, we found feasible solutions to the major challenges of implementing GLAO on Gemini. There's some compromises, but we don't think they're an issue. The concept we have supports all instrument ports, doesn't take up an instrument port, and incurs absolutely no throughput or emissivity penalty. It's very well integrated with the telescope. But just to stress, this is a pre-conceptual design stage feasibility study. Many questions do remain unanswered, and continuation to conceptual design stage and beyond is not currently funded. The idea here was to basically be ready to go if a funding opportunity arises. And we think we have a viable concept ready to go that should be good to go to conceptual design phase should the opportunity arise. Okay, thank you.
Thank you, Paul. Let's see, I see a question in the chat, but it's actually marked as having already been addressed there.
Cool.
I do see another, yep, yeah. This is the good thing about having colleagues online simultaneously there. Let's see.
Awesome, yeah.
Navigate back. I do see a new question. Would it use only one NGS with either P2 or OI WFS, or ideally you'd like to use more? The plot showed 3.
So we haven't really done the modeling to that level, but actually we would expect that one would probably be fine. but well, maybe I'm speaking a bit ahead of myself there. We haven't really modeled this. Hopefully one would be fine. We don't really have anywhere to put extra NGS wavefront sensors without vignetting the science beam. So we're kind of hoping one is good. It's GLAO, so the isoplanatic patch, if you like, or the iso tip tilt patch is pretty large. So it's really only tip tilt we're looking at here. In an MCAO system, if you're a multi-conjugate, then you need multiple NGS stars because your plate scale modes are unconstrained. We're a single conjugate system at the ground layer. So there is no degrees of freedom in plate scale in the DMs. You know, you need two M's to do that, two DMs to do that. So hopefully one should be adequate. I wouldn't imagine that tip tilt variation across the field would be significant at the level of correction we're looking at. Remember, we're not looking at a high Strel ratio correction. We're looking at a factor of 2 in image quality. So the isoplanatism errors in tip tilt would probably be pretty small compared to those introduced by the high level uncorrected turbulence, for example.
Great, thank you. And with that, it's going to be time to move on to the chat session. So thank you, Paul, and thank you to all of the speakers in today's sessions. We very much appreciate it, and we appreciate everyone who has been attending and listening in here. Janice, do you have any announcements before we move on to the chat sessions and then the TOO workshop after that with Brian Miller?
Nope, I don't have any announcements. Joe, anything on your end?
Just to make sure to come back for Brian's workshop after the chat sessions. I'll be here waiting.
Perfect. Perfect. Thank you, everyone. See you at the TOO workshop and see you in the sessions tomorrow. Thank you.
Hi, Brian, a quick mic check.
Sound okay?
Sounds good. Perfect.
Okay, I think we'll get started. The numbers are slowly going up. Looks good. So I'll start the introduction. So welcome to the Targeted Opportunity Workshop. This is going to be sort of a low-level look at resources, current procedures, and future for targeted opportunity observing. So looking at the nuts and bolts and doing some demonstrations. So it'll be a mixture of presentation and demonstration, some of which you may be able to follow along if you have a Python environment ready to go. Other logistical things, keep putting your questions into the HOVA chat, Q&A chat room, and we'll stop occasionally to look at those. I will not be able to answer any questions right now about individual problems with running the software. I'd be happy to follow up with people afterwards about that. Okay, so converged on the number of participants. So we'll get started. So as most of you are well aware, for most Gemini programs, the targets have to be included in the proposal. They're approved by the NTACs, and then you need special approval to add any new targets to your program. But with the TOO, or Target of Opportunity mode, the coordinates of the targets are not known at the time of the proposal, or the time that your observation needs to be scheduled can't be specified. For example, you're monitoring some source that needs to change state, and then you want to get spectroscopy of it when it changes state. So this TOO mode, of course, is useful for time domain astronomy, but it's not necessary, as I mentioned, and you may be waiting for optical survey to get some galaxy targets, for example. So it can be used for a wide variety of things. So you have to apply for this special mode and then get that approved by the NTACs instead of the exact targets in your proposal. So I will go through the two main flavors of target of opportunity observations. One are the rapids, which have to be observed in the next 24 hours, usually for that night or the night that's coming up. Because these are high priority observations, they usually need to be put in band 1, the highest ranking band, and they can't have any condition constraints. If there are any condition constraints, the chance of being able to observe at any given moment would be very, very low. It is possible to interrupt ongoing observations. Doing this back in the days of following up gamma ray bursts, the fastest time from receiving the trigger to start of science was about 6 minutes. So it can be relatively quick. You do need to specify in your proposal if you need to do this so that you can get approval for this particular mode. And if you do this, your program might get charged for any time lost to the program that you're interrupting, just so you know in advance. The other flavor of TOOs are the standard TOOs, which can be basically scheduled almost at any time after the trigger. It's usually for the next natural plan. It might be for the coming night if you submit the trigger early enough in the day, but there's no big urgency. You can set timing windows, usually days to months. And if you do a standard TOO follow-up of a rapid, then you need to have conditions better than any. It is possible to do standard TOs with LGS, but you need to submit your trigger at least 4 days in advance so we can go through the process of the laser clearinghouse approvals. Now, instrumentation, all the facility instruments really can do TOOs, but the workhorse instruments, which are almost always mounted to the telescope, are the most useful. In the optical, of course, that's the 2 GMOSs. In the infrared, that's GNIRS and Flamingos 2. For GMOS, it does have exchangeable components, especially the gratings. So the most useful for TOOs tend to be the B600 and R400 because they're almost always in And it's the third slot that gets swapped out between like the R150, R831 grading, B1200. So recommended to use the two that are in almost always. UOs can be done by some visitor instruments, but the availability is more limited. Some of them are block scheduled, or we might not have as many people trained up to use them. So you should check any given call for proposals to see which visitor instruments are available for TOOs. Some of which have done it are Elopeke and Zoro and Igrans. And it's important to know about the policy for competitive TOOs that we developed after the gamma ray burst kilonova. The gravitational wave kilonova follow-up from a few years ago, when we had about 6 or 8 different groups wanting to observe the same thing at the same time. So we developed this policy to make it clear what we'll do in this case. Link is there if you want to study it, but the main points are that the pre-approved Q programs get priority over any director's time proposals that come in. If multiple TOO requests come in for the same target, then if there's time, we'll try to work with PIs to work out what to do. But if there's no time, we're just going to take some data and work out what to do later. But there are some rules, like the first TOO in will usually win. And if there are multiple requests for the same configuration, like the same instrument and grading, then we have the option of sharing the data between the people that requested. So you're getting ready to do a trigger, and there's some information you might want to check on our web pages before you do. There are pages that give the TOO status of each telescope. It says whether we're accepting TOOs on that night. For example, there might be classical run or might be a engineering shutdown. So these links down here give these pages like this for Gemini South. These are instruments are available until what date this notice is good. And then, and then also the 2 GMOSs have pages which give the main components which are installed, mainly the gratings and the slits that are currently in the instrument, so you know what to use for your trigger. Oh, I should also mention that the PDF of this presentation is in the session on Wahova, so you can get the links and use it for reference. Also, you might want to check the weather to see if one telescope might be closed or not, so you can decide where to send your trigger. So there are some links to various useful web pages to get the current conditions, humidity and wind speed, things like that. And satellite images also, with satellite loops are very useful for seeing if there's clouds for the 2 sites. Often it can be hard to tell from this whether we are open or not, or whether we could observe. So if you're in doubt, just send the trigger and we'll try to do our best to get it observed. Okay, so that's sort of the information you need to sort of send the trigger. Now, I'd like to go through the actual how it's done. So in general, the process is that you have to organize a set of observing templates, and then the process is to apply a target to a template and then submit it to our database for further action. So during the phase 2 process, the contact scientists will work with the teams to define these template observations for the different instrument configurations they're going to use. And they're set to a special status to on hold, which means they've been checked, they're ready to go, but then they shouldn't be touched after that. Then once you have a target that you want to trigger on, the sequence of operations is copy paste this template to make a new observation, fill in the target specific information, of course, the coordinates, position angle, look for guide star, that sort of thing. Put any special instructions in notes, upload finding charts. You set the observation to phase 2 status called prepared, and you sync that with our database, and that causes a bunch of actions to occur in our database. That is the trigger itself. So as you can see with these sort of screenshots, this can be done manually with the observing tool, or OT. but it can also be submitted programmatically via this URL API. You see a little bit of the instructions here. So basically, you construct this URL string, which provides information to the database with all the target information and the other target-specific information like I had on the previous page. And the ODB takes care of the copy, paste, and trigger action. And you can get more documentation and some example scripts at this GitHub repo. It's called GS Select, and we'll be going and using that later on in the presentation. So while not required, because the OT will do GuideStar search for you, checking for GuideStars is kind of recommended to ensure your observation is feasible. Guiding is really needed, like to remove wind shake, do tip-tilt corrections, and get the best image quality. And many of the guiders, like the GMOS OIs, have rather limited fields of view, so there might not be a GuideStar available at all position angles. So position angle is important, then you especially want to check. This GS Select script will allow you to do GuideStar selection outside of the observing tool. It uses algorithms similar to, not exactly the same, but it's the same idea as done by the observing tool. And the bonus is that it has a fine position angle feature, which we've never implemented in the observing tool, which picks the best GuideStar available and then sets the position angle so that you're sure to get that in your guide or field of view. I can show how that works a little later. This API is very useful, but it does have its limits. For one thing, it does not support non-serial targets very well. We use ephemerides for all non-serial targets, not orbital elements. One important thing to know, and with the current API, you can't upload this ephemeris file or specify that this is a non-sidereal target. It assumes everything is a sidereal target. So a few workarounds here in case you're going to use this for non-sidereal targets would be basically in the target, give the horizon's name and give some approximate coordinates to use for selecting guide stars. You need to use PWFS2 for guiding. You could, in the note, you could put the horizon's name and the target type. So then either the observer or the QC could do the horizons query to get the ephemeris and then search for guide stars and so on. And just be sure that the observer knows that it's a non-sidereal target. You could also use the note to put a URL, a link to any ephemeris file so the observer or QC can download that and get it into our system. All right, so that's the end of the first sort of presentation piece. So I was wondering if there are any questions on that part, and then before we dive into the first demo.
Okay, so right now, Brian, there are no questions currently in the Whova question and answer window, but I will keep monitoring it and let you know.
Okay, and you can interrupt me if needed.
Sounds good.
All right, so we'll dive into actually trying to run some code here in real time and install software. We'll see how that works. So we're going to go through an exercise of actually running GS Select and doing a trigger. And I'm going to try to do this in real time. So this is the part where you might be able to keep up with me if you've got sort of an environment ready to go. I will try to keep it separate from other things on your machines. You can delete this easily if you need to. So this should all work with Python 3.6 or newer. I recommend using Python 3.7, especially if you're going to go ahead and do the Tom installation a little bit later in the workshop. And so first thing, of course, is just start with some working directory. So I'm here in my Python directory, and I'm going to create a directory here to put everything. And then I'm going to create a Python environment to keep everything isolated from the rest of my work. And activate that. And now I'm going to stall it. It'll take a few seconds to download the dependencies and install everything, but this part's fast enough. The other thing I'm going to do is download an example script from this repository. That's done. There's that. And the help, the documentation for the API. So now we get into the configuration. This is the example triggering script. So the main things we need to change, personalize it, is that I'm going to set this flag to true. So actually do the trigger, actually set it from on hold to ready. If you kept this ready equals false, it would make the new observation and put all the target specific information in there, but keep it at on hold. So now I've got an email address. So associated with a user key in this one test program I have. So I'm providing the user key. And we have a program in our test observing database at Gemini North. So we can trigger at will in this program. It will not interfere with anything operationally. It only sends me email spam, nobody else. So I'm going to set the server to the Gemini North test ODB. Next, I have to give the OBS ID of the template. So I'm going to show you the program here. Here's my observing tool. Here's the program. These are the different templates which are set on hold. There's some GMOS standard trigger, a rapid trigger, and the spectroscopic acquisition. So I'm going to use one. I'm going to do the standard trigger here. And then all the target info has to be put in. And then, so I'm going to actually do this mode where it finds the brightest guy star and sets the PA such that you can reach it. Special mode. Other thing I want to do is that the title of the group, or it will stick the observation just to keep it. Separate from other things. If anyone is following along with this, you are free to trigger, just change the name of the group. Okay, I think that's all right. Just do some checking. All right, let's try it. All right, so it's doing the guy star search. It found one, so it's popping up a little sort of position editor type display here showing the target. There's the guy star, the GMOS field of view. I close that, and there it sent the trigger. It told me observation 31 was created. So I go to my OT. There it is. Observation. It's got all the information that I put in there. There's the guide star. Observing conditions, everything that was in my script is now in my observation, and that can be observed. And if I look at it here, there's the guide star. It looks like my other visualization. in the Python script. So that's all good. That's a basic triggering with this API. Let's go back here. But the triggers can also be done with other layers of software, including these target observation managers are called TOMs, and you'll be hearing about those a lot at this meeting, especially today and tomorrow. So it's basically a web application on top of a database, which allows you to manage targets. It allows you to, enter the targets into your database and then submit observation requests to different facilities. These were first developed for a lot of TDA projects, but they're useful for non-TDA projects as well. Anything, especially with a lot of targets, or you have a large team and you need to manage data access and things like that. They're very flexible. They can even, manage the data processing, the data visualization, the prioritization. And the Las Cumbres Observatory has developed a toolkit which makes these really easy to create and stand up. And the link is here to get them more information. And just a little bit about the context that these are used in. So let me make this bigger. This is sort of the time domain ecosystem which the community has been developing. We'll talk more about this tomorrow, but I just wanted to get the brief overview today. There are facilities that generate alerts. There are brokers like the Antares system we'll hear about tomorrow, which does cataloging and classification, and the TOMs fit right in the middle here, where teams use them to collect the types of objects out of the brokers that they're interested in, and then use the TOM to manage the observations that they have on the facilities on which they have time. All right, so now we are going to actually try to create TOM. I said this was pretty easy to create. I'm going to try to prove it. To install the software, you have to run these various pip commands. They don't take too long, but longer than I want to wait right now. So I've pre-downloaded them and have another environment ready to go, but I am going to go through the creation and configuration of the TOM. So I'm going to start with this. So there's created in that directory, and now I need to start edit some settings. First thing I need to do is add and then I can run this setup. Answer. Oops. One for sidereal, it doesn't really matter. Then you need to make an admin account. So add a password. And there, that's the basic is done. But now we need to configure it. So it knows about my programs and I'm available in my access. So again, we're editing the settings.py file. I may need a few settings down here. The main thing is I need to tell it here. There's under facilities, under Gemini, then I have to give it all the similar type of information that I gave in the other triggering script. So I am just going to chop out this whole Gemini section. And you can copy, basically paste this bit right here into there. So as you can see here, I have to give it the URLs for the servers, just like I did before. I've got to give it these keys. I've got the email address and the keys for authentication. And then I've got to tell it about, these templates, the programs IDs and the templates that I have with a little description for each one. I'm also installed some sort of special plugins, which I need to tell it about. One is an extra plugin for Gemini. There is a base or a very simplified version of the Gemini plugin that comes with the TOM toolkit, which is fine to use, but it doesn't support GS select. It doesn't support the guide star selection, just in order to reduce the dependencies in the TOM toolkit. So I've added this extra repository here, which does allow you to run the GS select. And you can get it from here. So in order to tell it about that, I need to comment out the built-in one. Tell it about the new one I just installed. And likewise, I installed the Antares plugin for the Antares broker. So I need to basically do the same thing. I think in order to use the Antares broker and the Antares client that connects to it, you need to email the Antares team to get API credentials, and the instructions for that are here. So that's probably something you won't be able to do right now. All right, so I've got the configuration file up to date, and now I can actually apply that by doing this migrate command. And then actually run it. Okay, so I can then go to it. And there's my TOM. I can log into it and I'm ready to go. That's it. I've got a customized TOM in like whatever, that took 3 minutes. So there really is pretty easy. And there are all kinds of course complications, extra things you can do. This is just the start. But we can have a little look around. There's a place to enter targets. So you have a little map of the sky. You can create targets manually, import targets from lists, do like Simbad searches to enter them. Of course, the power of this is to do queries on these brokers. So that's what we're going to start with. So a bunch of different brokers that you can connect to. I'm going to use this Mars broker, which has a ZTF alerts that was managed by Las Cumbres Observatory. So I'm going to search for one particular ZTF target that I know about. I'm going to call the query that, and I'm going to look for this ZTF object ID. So I submit that. So that created the query. Now I'm going to run the query. It's Mars broker. So here's all various events for that target. And if I click view here, then it opens up the Mars broker and you see there's the object. It looks like some sort of merging galaxy with sorts of tidal tails and shells with maybe some sort of variability in the center, maybe AGN. Now let's try to observe that. So we go back here, we need to put it into the database. So I'm going to select it there and create target. Do this page and I just save it. So there's the observation in the database with the basic info. You've got the view of it. And now I'm going to want to observe it. So I'm going to go to the Gemini tab. This brings up the form for doing the manual observation submission. So first there's an elevation plot here, and we can see these are the different sites that it knows about. And this is setting very early in the night at Mcconaughey, so it should be observable. So here is the form. You can fill out all the parameters for the target. You can enter the guide star manually if you want to, or it will do the search. So this is sort of what I will do. I'm going to actually do a rapid trigger now. Give it another group name. I'm also going to use this find position angle mode. It's about 18.7 magnitudes in brightness. I'm going to give it an air mass constraint so it can go a little lower than the normal. I can update the exposure time. Yeah, I could enter a note there. So now let's just try this out. Oh, another thing I want to do is I actually want a P2 guide star instead of OI guide star for this one. So let's submit. Again, it's going off doing the guide star selection right now. There, I think something happened. And there's the observation entry in the database. See, here's the observation that was created. It gives the observation ID here. Go over here. This was actually a rapid. So this is the pop-up that the observer gets when there's a rapid TOO. So I can view the observation, see if I need to do anything with it right now. And there it is. There's the P2 guide star. I've got my air mass constraints. Changed my exposure time. All looks good. All right. So I think we are now down to, yeah, there's the results. So that's basic manual triggering with the TOM. Of course, advantage of this is that you can do a lot of automations in the TOM toolkit. It has, of course, APIs, so you can actually control the TOM toolkit from external scripts, including Jupyter notebooks here. So I'm going to go through a little example of that. I've got my notebook running over here, so I can just go through. And this is going to do a query using the Antares client. There's this particular target I'm interested in, so I'm just going to query for that. And go down here, there's some information about it. Going to, and then here's sort of in code, this is sort of like our first script we looked at of defining the details of the observation. Is basically a way of programmatically filling in that form in the TOM. So I'm going to tell it to use, it's this northern target, so it's going to use these two observation IDs. This is the standard science observation plus the acquisition. I give the target information. I'm going to do exposure times, various notes, air mass constraints. That validate looks good. And now we actually submit it. There's two got submitted, and I'll just enter those two into our database. Keep track of it. I go over to the OT. There, I've got the two observations. That's the science and the acquisition. So multiple ways of triggering with TOMs. And it's the automation that makes it really powerful in conjunction with querying the brokers. So we've triggered a whole bunch of observations. We hope we get a lot of data. Then once we get data, we actually want to get the data out. of the archive, hopefully do that in a programmatic way as well. And there are APIs to do that. I'll go over just briefly a little. I'm not going to go on much of this, just for information and some references so you can look up more information. The archive has RESTful APIs, which allows you to do things like doing searches, downloading files, looking for calibrations and things like that. So it's just one example of a query you can do, and some other potentially useful information, various libraries you can use. This URL gives the documentation for those APIs. And these are used now to make the GOA accessible via Astro Query. So take a look at this link for instructions for that. That can be extremely useful. Also, a couple of years ago, while I was playing with these APIs, I wrote this other little Python library, which mainly is like the communication boilerplate you don't want to repeat all the time. So that might be useful to some people. So it's available here. And this old presentation from a workshop on the Tom Toolkit gives some examples of how to use it. Okay, so that is TO triggering on Gemini now. So before I go on, it'd be a good time to stop and see if there are any questions.
Okay, let me refresh my Whova window, Brian. My window is giving me a blue thing. If Joanna can hear my voice, Joanna, are there any questions in the Whova Q&A?
No, I don't see any.
Excellent, thank you. Please continue, Brian.
Okay, very good. Since actually I think we're doing pretty well for time, I am going to go backwards a little bit and do one other example with the Tom to show, again, using Antares. So I'm going to actually use this Antares plugin that I installed and just show how that can be used. So I'm going to call this query Nova test, and this is going to use a filter that Monica, who'll be talking tomorrow, made. Define all these have been defined under tags, and Nova test filter, which that she explained to me is designed to find things that are getting bluer in time. The light curve gets bluer in time, so it's designed to try to pick out supernovae. So I'm going to make that query, and then I'm going to run it. Takes a few seconds. You can get a lot more information on the Antares website about how to create these filters. Okay, there's the list. Now we can look to see if there's anything useful here, anything interesting. So you get nice light curves like this. So that might be something that, an interesting supernovae. So the triggering process would be the same as before. Create the target and so on. I just wanted to show that the Antares query in action. All right. All right, we're going to finish up by describing a little bit about the future of targeted opportunity at Gemini. And we'll go over sort of the bigger picture of this tomorrow, but a little bit some of the more details of what we're planning for in the next few years. We do want to improve our TOO capabilities as part of ongoing Gemini program platform and the Gemma projects. These are major software efforts to try to make proposal and phase 2 preparation just much easier. Basically, we're going to be replacing the phase 1 tool and the OT and most of the other high-level tools. Really, we need to add new features that are just not possible in the current code. And by doing this, we allow a lot more automation. The key is making the system more API driven. It also allows us to make the code more maintainable, scalable. We're going to be producing an automatic queue scheduler to handle the scheduling part of it. And there's real-time data reduction. And we'll go over more of that tomorrow. And you heard some about that from Kathleen today with Dragons. And there's more information in these Gemini Focus and the NOIRLab Mirror newsletters. So the fundamental improvement for time domain is to make all the relevant information accessible via APIs. We don't want any more of having to go to web pages and look at them or try to scrape them into a script. So everything from the telescope status, instrument components that are available, the weather, information about your programs, all's got to be accessible easily programmatically. And it's going to be possible to basically do everything programmatically that you can do with the UIs that we're also developing. So all these sort of things, you can query configurations that match requirements. That's one of the main concepts that we're building up. As you can see right here, the idea is that you enter, for example, spectroscopy mode at a certain wavelength, a certain resolving power, a signal to noise, and we'll give you a list of all the Gemini instruments and modes which meet those requirements, and you can just pick them from there. So you don't have to go digging through lots and lots of instrument web pages. You'll be able to run the ITC. That's going to be fundamental part of all of this. Running the guide star queries, basically replacing that GS select script, will just be built into the system. Be able to create, modify, and submit and retract the observations programmatically. You won't have to go into the OT. There's really almost no way to retract an observation now without just emailing the QCs and saying, oh, I don't want to do that anymore. Another fundamental concept is it shouldn't be necessary to create these on-hold templates. I think it's maybe possible to still do that if you want to, but the idea is that you be able to create observations from scratch using our automation. And of course, we'll have full non-serial target support and uploading, downloading all the attachments, such as the ephemerides, math design files, finder charts, all of that will be supported. Now, the native APIs that will be used by the UIs, which is these, is a system called GraphQL, which is very flexible and is very useful for these web applications. But it's a little different syntax than sort of RESTful APIs that we're used to, like is used now for the archive and the API for the database I showed earlier. So we're going to have to do some training and things to help people out to get going with this. Giving examples, maybe developing some Python libraries to make some things easier to use, and give you some canned queries that are used very frequently. There'll be a new Tom Toolkit plugin, which will hide all this detail, so it'll look basically the same as it did before. And we'll be in discussions with Las Cumbres, we're working with on Aeon, as I'll talk about tomorrow, to try to develop some standards so that people learn the system once, you learn an API once, and it'll be applied to a bunch of different facilities. So we're hoping to start early testing on that next year and get the whole system operational by 2024. So it's still a few years away, but there's a lot happening on it now, and keep an ear open, keep an eye open for opportunities to test this out. And with that, that's basically it. Just in summary, the current TO trigger process is just based on adding targets to these template observations, a manual mode, and this programmatic mode with the sort of basic API. But you can do a lot with it. There's a Tom toolkit that's very flexible, lots of different ways to automate it, even with the existing limited APIs. In the future, we're going full API. I mean, programmatic access is the way to go. Automation and doing all this stuff without a lot of manual interaction. That's the only way probably the community will be able to handle a lot of the increases in alerts that we're going to be getting, and to do things rapidly. For example, if you have gravitational wave follow-up or fast radio burst, something like that. So that's just the low-level stuff. We'll talk more tomorrow about sort of higher level and go in some different aspects of what I mentioned here. So, but I'm willing to take any questions.
Excellent. Thank you so much, Brian. We do have a question here posted by Monica. Monica asks, is there any plan to integrate dragons with the TOM?
It could be. I think I know that various groups who are using TOMs use the TOM to manage their data reduction. So I would imagine, given that Dragons is Python, it ought to be straightforward to integrate those. We don't have any plans to do it yet, but a science team should be able to do that. Or it's something we can try to help out with down the road.
Okay, let me refresh one more time and see if there are any additional questions. Okay, I don't see any additional questions, Brian, but you do have 13 more minutes if you'd like to continue to add anything else.
I think I've covered all I've prepared. And so we can end a little early if there are no other questions. I've also got sort of chat times tomorrow. If anyone wants to talk more about this or needs help with running some of the software, getting things configured, so please sign up.
Thank you so much, Brian. Brian Miller. Okay, so if you have not signed up for Brian's chat session, please make sure you do that so that he can answer any additional questions you may have. Excellent presentation, Brian. Thank you so much. And with that, I will send it back over to either Janice or Joanna.
Well, thanks everybody. And thanks, Brian, so much. And we'll see you back here tomorrow for day 4. And don't forget the picture after the panel. Be prepared to turn on your video. Have a good evening. Bye-bye, or morning.